Hello everyone and welcome to day 2 of DataEngBytes, a community-built conference that showcases the best of data engineering right here in Australia and around the world. My name is Katie Peterson and I am a software developer with a passion for data from ThoughtWorks based in Sydney. My co-host today is Noel Hansons. Please introduce yourself.
Thanks, Katie. My name is Noel Hansons and I am the Data Engineering Manager at Lifeblood based in Melbourne. I love leading data teams, data communication, and data governance. I also run the Data Engineering Meetup here in Melbourne. Let's do an acknowledgement of country to get us started. I acknowledge the traditional custodians of the various lands on which we meet today and the Aboriginal and Torres Strait Islander people participating in this online conference. I pay my respect to elders past, present, and emerging, and recognise and celebrate the diversity of Aboriginal peoples and their ongoing cultures and connections to the lands and waters of Australia.
Today we have a jam-packed schedule full of incredible talks. First up, we have Gian Merlino with Some Like It Hot. Then we have Caito Scherr with Sweet Streams Are Made of These, Data-Driven Development in Stream Processing. Then we have Joel Roland and Steve Lee bringing us ETL and data ingestion made easily, followed by Sam Harley talking about how MongoDB enables real-time data with event-driven architecture.
Following that, we have Larene Gassick speaking about inclusive storytelling with data, Aiko Klostermann speaking about artificial intelligence, more like artificial stupidity, and Kerry McRae speaking about building data integration services for real-time on AWS. All talks today are pre-recorded, but most of our speakers will be joining live right after their talks. Our speakers will answer your questions via Slack and also live once they join us. Today it will not just be Katie and I talking. We have a number of guest hosts who are also our co-organisers who will join us at different times and conduct QA sessions with our guests. So it'll be fun and I'm sure we're going to be entertained and learn a lot as we go through. An event like this is only possible with the support of our wonderful sponsors, so I'd like to take a short moment to acknowledge and thank each of them for supporting DataEngBytes. Snowflake, MongoDB, Databricks, AWS, Fivetran, Confluent, Microsoft, ThoughtWorks, Instacluster, Canva, Yao, and Cloud Shuttle.
We will also make sure all the talks are public after today, so if we do experience any technical issues or if you miss a talk, you'll be able to watch them later too. It is important to remind everyone we do have a code of conduct, so please be thoughtful and kind to each other. Please act with respect and behave. We have moderators on Twitch and YouTube to make sure everyone adheres to our code of conduct. Finally, we are going to be distributing surveys, so please fill them out as feedback is really important. It will help us figure out how to make the event better next time. We always love to hear from data engineers and those wanting to get involved in the local community.
Well, let's not waste any more time. It's time to welcome our first guest, Gian Merlino, who will deliver our day 2 keynote with his talk, Some Like It Hot.
Hello, everybody, and welcome. For my talk called Some Like It Hot, I'm here to talk about how data fits along a temperature spectrum and how thinking about it that way is actually really useful when selecting which kind of data system you want to use. I'm also going to talk about how thinking about this temperature spectrum provides the key to that question you've always been asking yourself. How come it seems like I can never find the perfect system that solves all my problems? So, who am I, and why should you listen to me? Well, I'm Gian Merlino, and you don't have to listen to me if you don't want to, but why you might want to. I'm committer and PMC chair at Apache Druid, which is a big data project used at some of the largest internet companies today and a variety of other industries as well. I'm a co-founder at Imply, a company built around Apache Druid, and we're hiring, so please feel free to come talk afterwards if you're interested. And I've been working for the last decade or so on scalable data systems. And a lot of that's been spent in the analytics space. So it's a space I'm definitely very interested in. So today, what are we going to talk about? I'm going to talk about how data fits along that temperature spectrum that I was talking about earlier, from cold to hot. We're going to go on a tour of data systems over the years and talk about how things have evolved, how they've scaled, all that. the project I worked on, Apache Druid, we're going to meet Apache Druid and see how it fits into the space. And then we're going to ask ourselves, can we have it all? The thing that we're always wondering, is there one system that does it all? The answer is, of course, maybe. So first off, what are things you might care about? Well, the spectrum, as you might have guessed, from cold to hot, is a spectrum mostly about performance. But there's other things that relate to performance and how we think about it. So on the top, we have this beautiful bowl of hot Cheetos and Takis representing hot data. On the bottom, we have a warehouse of government cheese. It's even in black and white, representing cold data. For hot data at the top, we're thinking query speed sub-second to just a few seconds. We're generally going to want to be working with data as fresh as possible. It might be true real time, might be near real time, might be data that's loaded within the past few hours, but in general, we want to care about fresh stuff. We're going to have high concurrency. So these hot data sets are data sets that part of the reason they're hot is because they're so critical to the business that we want to put them in front of a large number of people, not just professional data people, but end users, product managers, marketers, that kind of thing. And the use cases are going to be highly interactive. So people are going to be spending a lot of time inside these tools. They're not just going to be getting a report and leaving. They're actually going to be doing a lot of investigation. We call this OLAP, online analytical processing. On the other side of the spectrum, the other extreme, cold data, slow queries are okay. We might not care how slow they are. We might be okay with minutes or even hours. Less fresh data is okay. We're doing a lot more reporting, a lot less operational stuff. Generally going to be low concurrency. We're not going to have that many people using this. It might just be our professional data people. And the use case is more oriented around reporting and planning, less around being highly interactive. So this is a tool that we make at Imply. As you might have guessed, at Imply, the Apache Druid project, we're all about hot data and fast stuff. And so this is a tool we make called Imply Pivot. It's the making a tool like this work properly is actually what inspired us to create Druid in the first place. We wanted to build something that was able to power this kind of interactive experience, even at scale, even on massive amounts of data. And why does this matter? What do people do? Why does this ability matter? You might call this real-time OLAP. And the two use cases that fit into it are exploration and monitoring. Exploration meaning I want to drill into my data, I want to do iterative questions, I want to understand what's happening. And then monitoring meaning I want to know what's happening right now, observability. These two things come together to build these real-time OLAP workflows. So that being said, where does it matter? These hot speeds are useful in a variety of applications. Some of the ones that we've seen people adopt Druid for are the stuff on this slide. So risk and fraud analytics, useful because there is a need to dive deep into things to figure out what's going on. Data-driven applications is a really big one. That's a case where concurrency is going to be very high. You might have a large number of people outside your organization accessing a data-driven application. Network performance, another one that tends to be very operational in nature. The real-time, fresh aspect of things tends to be very important there. Clickstreams, similar situation. Freshness matters for understanding rollouts of new products, doing A/B testing. But even the ability to do a lot of exploration over historical data is very interesting when trying to find trends and figure out what your users are doing and how they're behaving. Digital advertising, the market everybody loves to hate. Although it did bring one nice thing to the world, which is it's been the genesis and inspiration for a lot of interesting technology that we see around us in the big data world. And Druid's actually no exception. Druid was originally created for a digital advertising problem. It's a space where there's even the smallest players, even the smallest advertising companies generate a truly tremendous amount of data. And so the need for tools that are scalable and efficient is immense. So we can at least thank them for that. Data warehousing, a situation where you might have a data warehouse that you're looking to expose to more people. You're looking to make it more real time. You're looking to get more applications built on top of it. And so you're looking for a platform to make that happen in a performant and available way. Metrics, so your sort of time series metric store type applications. There's actually a lot of overlap between the time series world and the analytical world. They're coming into a collision over time, I believe. And then IoT, we've seen it come up a lot there as well, where the number of devices can be truly incredible. So these are all a variety of situations where the scale, concurrency, number of users you want to get in front of, amount of exploration that needs to happen, amount of observability that needs to happen, mean that you want to treat them as hot. So that demands a question, which is, why do we want to tolerate cold data at all? Why not make everything hot? And of course, the reason is cache. The reason is that making large amounts of data available at hot speeds is something that costs money. It requires memory, it requires hardware, it requires network bandwidth. And the business case to spend that kind of money may not be there for everything. So let's take a little bit of a stroll down memory lane and look at the architecture of these systems and how some systems evolve to become hotter, some systems evolve to become colder, and what drives that. It all starts at the beginning. It all starts with a single relational database, one size fits all. You've set up Postgres, you're using it to store your shopping carts, you're storing your products in there that you're selling on your e-commerce website. And it works great. You're doing your analytics on your production database because you don't have that many customers yet. Why not? You don't have that much data. But at some point, this stops scaling well, and you stop being able to use a single database for everything. So the next thing that's going to happen is you're going to build a data warehouse. You're going to build a data warehouse. You're going to have your relational database is now going to only be used for what we call OLTP, online transaction processing. It's only going to be used to power the actual application or the actual business case that you're offering. Then you're going to develop some sort of ETL, extract, transform, load process. I apologize for the acronyms, but this is an area that's rife with acronyms. You're going to load that into your data warehouse. And your data warehouse is something that's going to enable you to do really the same kinds of analytical queries you were doing on your single database. But by offloading it, you are minimizing the production impact of doing these analytical queries. And you are potentially getting the ability to do these analytical queries in a more scalable way. But one of the issues with the old school data warehouses is, you'd have a tough time scaling them too. You would put a lot of data into them. They would get slower and slower and slower as you added more and more data. And eventually they'd be too slow to really use in the way that you want to use them in. They become ice cold. And you want to warm them up a little bit. And so the way that people back in the day would warm them up a little bit is put things into a OLAP database, an online analytical database. And this would be a subset of the data. It might be a summarized version. It might be just a few tables. It might be coarser granularity, like you might only have daily aggregates instead of having the raw data. But you do something to it to make it more manageable and put it into an OLAP database. And now that's hot again. And now you have your situation where in this architecture, which was very popular in the 90s and early 2000s. You have a data warehouse where you have sort of all your data cold, but it's all there. Your OLAP database where you have some of it, or maybe it's summarized, or maybe it's not full fidelity, but it's available hot. And then big data happened. Then we hit the mid 2000s, we hit 2010. It's time for big data. And everything started to scale out. Your single relational database, no one's doing that anymore. Now everybody has sharded relational databases. Instead of putting all your shopping carts and products in one database, you're going to split them up by customer. Instead of having a data warehouse, now you have a data lake. And your data lake is going to be either a Hadoop-based data lake using HDFS. It's going to be a cloud data lake using S3, something like that. It's pure storage. Getting data from the thing that runs your business to the thing that you're going to store it in. You're going to have some kind of ETL process again. Could be change data capture plus Kafka. So it could be that you can use, for example, Kafka Connect to capture change logs from your relational database and dump them into Kafka and get them from Kafka to a data lake. There's a lot of ways to do this, but one way or the other, you're getting it in there. And then you have a scaled out query engine. And the scaled out query engine enables you to do the same kind of analytical queries you could do from your old data warehouse, but now you can do it from your data lake. So everything's scalable here. The sharding allows you to scale out the transactional database to your heart's content. The ETL processes are all scalable as well. The data lake is, of course, scalable storage, and then the query engine is scale out processing. So everything's scalable and beautiful, but it has a downside. It's slow. it's actually really slow. It's actually slower even than the old system. It's more scalable, but we've sort of paid a devil's bargain to get that scalability. We've slowed everything down. Now we're in the world where we're using query engines like Hive and like Presto, and they work well enough, but these queries on large amounts of data are taking quite a long time. So something that a lot of people start doing, and this becomes popular, really popular in the mid 2010s, just a few years ago, is storing an optimized copy of your data in a serving database. One of the earliest things that got really popular for this was Cassandra. HBase is also pretty popular. These serving databases are going to store an optimized copy. This will sound a little bit familiar. It's a little bit similar to the technique used in the pre-big data era with the OLAP databases. These serving databases are going to store some kind of optimized copy of your data designed for hot access. A lot of the ways that people did this, like I mentioned in the early days of big data, were with key value stores like HBase and like Cassandra. And this is where Druid comes in. What we've done with Druid is we've tried to build the best serving layer that we could possibly think of. And that means a few things. It means that we are targeting very high concurrency. We're targeting very low latency queries, but we're also targeting a lot of flexibility in the kinds of queries you can do. So one important thing about Druid that we'll get into in a few slides is that it's actually not a key value store. It's based on a underlying column-oriented data store. So it's the same kind of columnar storage that you would see in a data warehouse or something like an ORC file or a Parquet file. But on top of that, we've added indexes. We've added the ability to do streaming ingestion. We've added the ability to do batch loads from data lakes. And we've added a whole suite of resource management features that are designed to give you the kinds of performance you're looking for, even under highly concurrent workloads. And what that means is that in your data architecture, Druid is going to fit into this hot analytics area of the stack. You may still be using a query engine for your colder data and your warm data, query engine like Presto, like Hive, like a cloud data warehouse. And you'll be using Druid for things that have these hot requirements. One interesting thing there, of course, is why don't you use Druid for everything? Why don't you use a query engine for everything? Why does it make sense to have both? And we'll talk a little bit about that in the later slides as well, as we start to explore this idea of why can't we have it all? Can we have it all? Where are we getting with this? But I'm getting ahead of myself for now. Let's just talk about Druid. So the reason people use things like Druid is because they're looking to power analytical applications. And it's especially interesting to use a technology like this for analytical applications, because if you have any of the problems of scale, of high concurrency, of streaming ingestion, of wanting to provide people with a lot of observability, but also the ability to do a lot of ad hoc exploration, it's really important to have a system that scales well, that performs well, that's able to power that stuff. So people have put a lot of applications on top of Druid over the years. On the left, of course, you have the one that we built at Imply, Pivot. On the right, there's other applications that have official support added for Druid: Looker, Metabase, Apache Superset. SQL, of course, not an application, but you can query Druid using SQL, and you can use that to make your own custom applications. Druid is used pretty extensively in the wild. The project's been around for a few years, and a lot of the earlier and biggest adopters were tech companies in Silicon Valley. And of course, the reason for that is because these tech companies are some of the first to have these big data problems and to have these big scale problems, and some of the first to adopt technology designed to solve it. So Druid used at Netflix for real-time insights on experience, used at Mopub, which is a Twitter subsidiary, for querying terabytes of data in seconds, and used to power analytics at Airbnb as well. What all these use cases have in common is they're huge and performing very well. So ingesting 100+ billion rows per day, retaining trillions of rows, year of retention, hundreds of servers, query latency sub-second to a few seconds, and a mix of streaming and batch ingestion. And these kinds of folks are using Druid because it's fast. It's fast. We do a lot of internal benchmarks, of course, but the ones that you should trust most are the ones done by third parties. And this is some data from a benchmark done by an academic database research group showing performance of Druid on similar data sets versus Hive and Presto, some SQL query engines. And you can see pretty massive differences here, 20 to 59x over Presto and 100 plus x over Hive. And so what's going on here? Why does this happen? Druid, I said earlier, uses a columnar format. Hive and Presto can read columnar formats as well. Druid is integrated with the data lake. Hive and Presto can integrate with the data lake. What is the reasoning behind this? So to figure that out, we have to pop the hood and ask ourselves, how does it work? What's going on in there? So internally, Druid uses a microservice-y kind of architecture where we have a bunch of different processes responsible for a bunch of different things. And I don't want to go into a ton of detail about how each of these works, because I don't want to bore you to death, but suffice to say that you can get a full explanation in the docs. The part I do want to touch on is you see these little boxes everywhere, these little columnar yellow boxes everywhere. And these boxes are stored in deep storage and pushed in there by the indexers, pulled out by the historicals. These are processes in Druid responsible for reading and writing data. And what these little boxes are is we call them segments, data segments. Each one is a few million rows and is essentially a micro partition of the data set. So a really big data set is going to have thousands or tens of thousands or even millions of these segments. And what they give us is each segment is individually compressed and indexed, and the parallelization system in Druid is built by fanning out queries to all the segments involved in the thing you're trying to do. And then what happens inside them is really where the magic happens. So we built the fan out system just to fan queries out to thousands of segments per query. And then within each segment, we try to process those 5 million rows as rapidly as possible. And that's the key to performance. So I'm going to talk a little bit about a sample query and how it operates on the scale of a single segment. And then imagine that happening 1,000 times in parallel to get you the answer you need. And to do that, I want to talk about how the engine and data format are integrated. So there's a few things I'll talk about. One is compression. In Druid, we have a columnar format. Every column is individually compressed based on that type. Secondary indexes, that is one area where we start to differ from what a lot of query engines do. A lot of these query engines and query data lakes don't have secondary indexes, but it turns out to be very powerful. Operating directly on compressed data is also really important. Some of them do it to varying degrees. And late materialization is also critically important. This is a fancy database person term for saying don't read data you don't have to read, which is going to be a really common theme, as we'll see. So this is the layout of a Druid segment. A typical Druid segment is going to have a few million rows in it. This segment has 8, because that's how many fit on the slide. This segment has 5 columns. So in Druid, we store data oriented by column. The first column here is time. You can see it's long typed, 64-bit integer. The second column is artist. So imagine this is a table of ticket sales in various cities or various musical acts. So we've got AC/DC, Silverchair, we've got Perth and Sydney. The artist column is a string, and there's 3 components to it. The data component is, there's 1 entry there per row, and it's just an integer. So you see the first 3 are zeros, the second 2 are ones, and the next is 222. So what this is saying is it's a dictionary encoded string values. And so the first 3 rows being 0, 0, 0 mean that the first 3 rows of this particular data set have artist AC/DC in every of the first 3 rows. And then the next 2 are both Kylie, and then the 3 after that are Silverchair. We do this so it's a form of compression. So it makes the data section smaller, especially when the number of unique values is low relative to the number of rows in the segment, which is common for a lot of columns. It's not universal, but it's common enough that this is quite helpful. But it doesn't just perform compression, it also enables us to operate on the compressed data. So you'll see in a bit, but what we do is when we're doing a group by artist or group by city, we're gonna actually use these numeric keys to do the grouping rather than the strings, because we can process numbers faster than strings in a computer. So the next section is the dictionary. The dictionary tells us what each dictionary code means. And then the third one is the index, and the index helps us filter. So what the index is saying is there's going to be a single entry in the index for every entry in the dictionary. And they're corresponding 1-to-1, and it's a list of rows that contain that particular dictionary value. So the first section of the index is which rows have ACDC and so on. These are also stored compressed. They're stored compressed using an algorithm called roaring bitmaps. And we also operate on them in their compressed form. So if you want to do an and or an or comparison, we are actually going to combine two compressed roaring bitmaps together into another roaring bitmap. And finally, the last two columns, skip city. So the last two columns, price and count, are both numeric columns, just like the timestamp column. They're stored the same way. All right, let's do an example query. So here's a simple query. We want to look at all the ticket sales for ACDC, and we want to break it down by city, group by city, and we got to get the total price in every city. Straightforward. So a query like this is actually a typical kind of query you're going to do with a system like Druid. You're going to be doing some kind of filtering, some kind of grouping and breaking down, and then some kind of aggregations. These are the kinds of queries that are going to power these interactive analytic experiences we're trying to power. And we want to be very flexible in the kinds of queries we can do. So we want to be able to support any kind of filter, any kind of grouping, any kind of aggregations. And so because of that, we're not going to want to pre-cache anything. We just want to focus on computing whatever you give us as quickly as possible. So the first thing we're going to do is resolve the filter. And so we're going to go to the dictionary, and we're going to see what the code is for ACDC. The dictionary is stored in sorted order, so we don't actually have to read the whole dictionary. We can do a binary search through it to find the correct value, which is what we do. We see that ACDC is 0. The next thing we're going to do is retrieve the index for that value. So that's going to be the first row in the index section, because it's the first row in the dictionary section. And what we're going to see is we get a compressed bitmap that represents 0, 1, and 2. So the first 3 bits being set, representing the first 3 rows containing that value. So now we know which rows contain this value. And this is actually super important. This is one of the first ways that we start to differ from what a standard query engine on a data lake would do. A lot of them don't do secondary indexes because the way that you need to use secondary indexes involves a lot of random access, and it requires data actually being stored on the server. And we'll discuss this more in a bit, but Druid's actually prefetching all this data before the query happens. So it has the data stored locally, typically on SSDs with however much cache memory that you can. Doesn't need to all be memory, but we typically use a mix of memory and SSD. And we are able to, because of that, we're able to use these indexes. So, okay, anyway, we use the index. We know that rows 0, 1, and 2, the first 3 rows qualify for the filter that we're looking for. The next thing we're going to do is the aggregation. So next we're going to group by city and sum up price. And so the way we do that is now we go to the data section of the city column. You can see we have not gone to the dictionary, the index. There's no need. We just need to know what the first 3 dictionary values are. And it's 2, 1, and 2. And the first 3 prices are 1800, 2912, 1953. So we're going to build a little array, and we're going to use that array to aggregate these things. And the reason we're doing an array is because there's not that many cities. There's only 3. And so what we're going to do is we'll build a 3-element array, and then anything we see for one of the cities will go in that element of the array. If there was a lot of cities, more than we could allocate an array for, then we would use a hash table. So we choose hash table array based on how many things we anticipate grouping. Anyway, so that being said, we've chosen an array because there's not that many cities. It's going to have 3 elements. Because we don't know ahead of time what cities we're going to see, but we know there's only 3. We're only going to see stuff for Perth and Sydney, so only those 2 are filled in. Melbourne has a null stored in it. And that's the end of that. We don't have to read the rest of the data section of the city column because we know from the index for artist that only the first 3 rows contain anything we care about. We don't need to read the dictionary yet because we don't actually care what the city values are yet. We're just aggregating. The next thing we're going to do, now we're going to read the dictionary. We've done aggregation, and now we read the dictionary to see what the actual values are. And we do this after aggregating because typically when we're doing a group by, a lot of times the output of that group by, the number of grouped rows, is much smaller than the number of rows you're reading. And so it pays to defer this dictionary lookup until later. So this is this idea of operating on compressed data as long as possible. Anyway, at this point, we know that Perth and Sydney are the 2 cities, number 1 and 2, that we've seen tickets for. And so we can, at this point, we are done with the query for this segment. And let's look at what we've done. We've done a binary search through the dictionary section of one of the columns. We haven't looked at the entire dictionary even, we've just looked at pieces of it. We've done a single random access to the index section of that column. We have read just the sections of the city and price columns that we need based on the index of the artist column. We haven't read past the first 3 rows because we didn't need to. And we've only read the 2 values out of the dictionary using random access for the city column. So we've really been very economical about how much data that we've read from disk, from memory, how much we've had to transfer to the CPU, all this stuff. And this is where we get our performance from. We get performance from being extraordinarily economical about how much data to read and process. And then once we've processed each segment in an economical way, from every segment we have a partial result, and then we just have to merge them all together. This process in a well-running, smoothly humming Druid cluster, even on top of billions upon billions of rows, is going to happen in less than a second. But okay, I at the beginning promised to talk about why it seems you can never find the perfect thing. Can we have it all? And let's talk a little bit about that. So we have Druid, and I talked about why Druid's super fast. We're familiar with query engines, things like Presto and Hive. Why can't they do what Druid does? And why can't Druid do it? And why do you still need them in a world where Druid exists? Let's look at some of the differences between them. With Druid, we're doing batch ingestion and streaming ingestion. We're actually ingesting things because Druid is not just a query engine. It's a database. It stores a copy of the data. With Druid, data is fetched ahead of time, partitioned and indexed. And this ahead of time fetching, this indexing, this well partitioning and balancing of the data all contribute to performance that is beyond what a simple query engine on top of a data lake is going to be capable of. The query engine on data lake has one big advantage in that it does fetch data on demand. And fetching data on demand means a couple of nice things. It means you don't have to ingest it first. So if you have data in some goofy format to query it in Druid, you have to go through an ingestion process. Something like Presto can query it directly. It's not going to be very fast to do each individual query, but it may be quicker to get off the ground in the first place because you don't have to load a table first. This ability to fetch on demand also means that the elasticity can respond much more quickly. So Druid is an elastic system designed for the cloud, and you can scale it up and scale it down. Scaling it up is as easy as adding more processes. Scaling it down is as easy as terminating them. And the system will self-balance and self-heal in response to this scaling activity. So Druid is a totally elastic thing, but because we need to fetch data ahead of time and because we do have to balance data before a new server can be used, when you add a new Druid server, that server doesn't participate in queries for generally a few minutes to an hour or so. And what that means is that if you're elastically scaling it up, you will scale it up and you'll be able to use that new capacity. It'll take at least a few minutes for it to become available. Whereas a simple query engine that doesn't have any locally stored data, you could imagine spinning it up, doing a query, and then torching it down. So the elasticity can respond a bit quicker with that kind of system. Both, of course, have elasticity. They're both fault tolerant. They're both share nothing in the sense that the servers don't coordinate with each other, and they're both scalable to a very large degree. So it seems like they have a lot in common. And these differences, a lot of it comes down to, are we fetching data ahead of time? Are we indexing it ahead of time or not? The use case for Druid is you're going to get better performance on the same hardware. That prefetching of data, the indexing, the increasing efficiency. So the price performance ratio is really great with Druid. You're also going to get a lower performance floor. And what I mean by that is that you'll be able with Druid to get queries that are sub 1 second, even sub a few hundred milliseconds. Whereas with a query engine on top of a data lake, it's going to be really tough to get their query latencies that low. But the query engines are nice. You can have a lot of federated data sources in there. You can query things that were not previously ingested into that query engine. And you get spot elasticity. You get the ability to elastically scale up and down very rapidly. So can we have it all? The thought I want to leave you with is that while the use cases are very different, the architectures are not that different. We have relatively minor differences, like are we prefetching data or not? Are we fetching data on demand? Are we able to query data in something other than our native format? Are we building secondary indexes or not? Are we intelligently balancing or not? One reason that I really enjoy working on Druid is because I think it is a good platform for exploring these ideas. And I think it is a good platform for eventually building a system that is going to be able to let you have it all. And while we might not have that today, it's a world that I'm really excited about working towards. And with that, thank you, and any questions?
Thank you so much, Gian. That was a really wonderful talk. We do have quite a few questions that have come through on YouTube and Slack, so thank you for joining us today. The first question that's come up is, I'm interested in the history of software. While other data eng products have a famous history, Droid seems to be a bit more mysterious. Where can I find out more about its origins?
Well, one place is for me, I suppose. I was part of the original team behind Druid, and we originally made it at a tiny little startup that was in the online advertising space. And so, as I mentioned in the talk, that was the birthplace of Druid, and we built it because we wanted to power these kinds of interactive analytical applications on huge amounts of data. If you search around for history online, I'm sure you'll find it. I plan to put a link that is a blog post that talks about this in as much detail as you might like in the Slack channel.
Awesome, thank you so much. We have another question here. Could you draw any comparisons between Droid and ClickHouse?
I can. So Druid and ClickHouse are both open source database systems. I think they're more similar than they are different. They both have a culture of trying to be super fast. They both want to deal with huge amounts of data, all these things. They both store data in a columnar format. They use similar kinds of compression. So I think they're more similar than they are different. I think I don't really necessarily want to get into a feature comparison because it changes all the time. Like, these are both very fast-moving projects that are both constantly adding features. So maybe in terms of a good way to think about it is in terms of feel. I think that in terms of feel, I hope it's fair to say that ClickHouse might feel like something that's a ClickHouse cluster might feel like a collection of individual servers that, each server has some data and there's you query them that way. And a Druid cluster does not necessarily feel like a collection of individual servers. It feels like it's designed to feel like a cluster. And so balancing of data between servers in a Druid cluster is much more fluid, for example. There's no strong affinity of data to a single server. And that feels a little different, and it comes out in how you feel about and how things work operationally and how they handle fault tolerance and how they handle balancing. And so they tend to feel different when operated at scale.
Thanks, Gian. We've got another question from the floor here. Who are the early adopters of Apache Druid and Imply, and what industries do you find yourself working with?
Yeah, so the early adopters of Druid are the same early adopters of a lot of the big data stuff that came out around the same time. So we initially open sourced Druid in the early 2010s, and that was the era when all the big data stuff was getting open sourced, and it was all, the early adopters were all the internet industry. And no different with Druid. I think the very first user of Druid outside of our company was Netflix, and it spread from there. What we're seeing now is that outside of the internet world, there's an increasingly large number of people that want to be able to do similar kinds of things. They want to be able to do these really fast, interactive, analytical experiences and applications on top of huge amounts of data. And that's, I think, one of the earliest places that showed up outside internet was in telecom, anybody that has a website, retail, this kind of stuff.
We have another question for you. How do we compare performance of Imply with Metabase, Superset, Redash running on top of Droid?
Good question. So these applications all provide a pretty different user experience. The Imply pivot experience is very fluid. It's a large number of small queries being made incrementally and iteratively. The experience you get with some of these other applications is maybe a smaller number of bigger queries. So I would say that it's less about how performance differs and more about how the experience differs. At the end of the day, they're running on the same underlying database.
Thank you so much for joining us today. If you do have any further questions for Gian, please pop them in the Slack channel. We will be splashing up a QR code after this where you can provide feedback about Gian's talk. And yeah.
Hi everyone, my name is Karen Davis. I'm a lead data engineer at ThoughtWorks. I'm really passionate about all things data, and I especially love looking for ways to apply software engineering best practices to both data and machine learning. And it's really awesome to be part of this conference today. So our next speaker is Caito Scherr. Caito is a software engineer turned developer advocate at Vervica. She's previously worked on New Relic's mainstream processing team. And outside of tech, she loves running, woodworking, and terrible puns.
Today, she is going to talk about how to use data-driven development tactics to leverage the strengths of stream processing. Remember, if you have any questions for Caito, to ask them in her Slack channel. With Sweet Streams are made of these, data-driven development and stream processing. Please welcome Caito Scherr.
Hi, everyone, and welcome to Sweet Streams are made of these. Data and metrics-driven development for stream processing. My name is Caito Scherr, and I'm a developer advocate. I represent the US region for Vervica, formerly known as Data Artisans, the creators of Apache Flink. I'm based in Portland, Oregon, and I used to be a software engineer at a data analytics company. And I've been working with stream processing with Flink since 2017. So combining metrics and stream processing is something that I could geek out about for hours. It was very hard to cut this talk down to under 30 minutes. And that's what I'm here to talk to you about. Using data and metrics driven development with stream processing, including which tactics should be modified or really prioritized for stream processing. So data-driven development can mean a lot of different things. So I'm going to start with some basic principles that I'll be covering in this talk, as well as briefly a few fundamental concepts about stream processing for any of you that may be unfamiliar. Next, where to even get started. So how do you know what to measure, what's going to be the most helpful to you, and how do you figure that out without spending a lot of time and energy on it? I jokingly, but also seriously, like to think of this as metrics-driven metrics. And that's going to be kind of the bulk of this story today. Lastly, stream processing has some additional challenges in how it impacts the surrounding ecosystem that are just kind of unavoidable. So this part's going to be fairly short, but I think it's important to end with some metrics about where those integration points come into play and using metrics as a shared language to minimize some of those challenges. So briefly going over some of those basics. If you Google the title of my talk, maybe not the pun version, but the subtitle, you probably notice that there's a lot of terms, a lot of different interpretations and opinions on each of those terms. And if you search specifically for data-driven development, you'll most likely find information about business metrics and data-driven design. And there's actually a pretty big overlap between those two, as essentially the main focus there is using data to drive the design of a product that customers actually want to buy and use. So it's important to note the differences between the two though, because that's going to really change how you use your metrics and who's actually going to be using those metrics internally. Business metrics refers to anything related to internally measured success. So team velocity, sprint burn down, lead time, those sorts of things. Business metrics can also include what some people refer to as vanity metrics. Vanity metrics often include things like, we're putting out 3 million messages through a day. Things that are very impressive, that look really good for press releases and blog posts. Data-driven design relates specifically to the end user experience. As the name implies, the main focus here is to use data, typically data involving usage patterns and user feedback, in order to better understand and design for the needs of that user. Data-driven development is often kind of lumped together with these two or used as an umbrella term. I do think it can still be appropriate as an umbrella term, but my focus in this talk is where it represents metrics that are targeted at changing the development process itself. So that's what I want to talk to you about today, because I think it's just really essential to be able to look at that on its own in order to really leverage it properly. Secondly, there's a set of principles that come more directly from data-driven design, but they're relevant in all of these areas. It's this idea of a three-tiered approach that defines the type of metrics you use and how they guide your product, but categorized by their relationship with quantitative or qualitative data. Data-driven design is centered purely around quantitative data. This process is applicable to aspects of the software design like optimization and performance. As you progress outwards, you next have data-informed design, which weighs and utilizes qualitative and quantitative data equally and usually together in order to make a design decision. Furthest out is data-aware design, which is typically focused more on directly qualitative information, but quantitative analysis is often still used as a base or to pair with customer use stories, detailed feedback, or discussion-based risk-reward analysis. This category is often thought of as one that takes the larger picture into account, which is why this diagram is often portrayed more like a circle like this. So I like using both of these, but the value in this one specifically is that it really shows that wider scope where it takes progressively more types of data into account. It's also important to say, because this will come up later, that typically development styles in the center tend to be much easier to automate, whereas the further you go outwards, the more and more manual those processes will likely have to be. This is also particularly relevant for how to share metrics effectively with different internal teams and groups as you get closer or further from the engineering team that's at the center of that project. Lastly, very short review of stream processing. So a lot of you are probably familiar with stream processing, so I will try to go through that pretty fast. Okay, so as the name implies, stream processing involves a continuous stream of data. This is used primarily as a distinction from batch processing, where data is published as a system to a system or application in bounded units or batches. With a continuous stream of data, there's a lot of benefits. Most data is actually already best collected this way, whether it's input from a video game, weather sensor readings, or customer usage patterns. And without breaks or having to wait for new batches, it naturally has more potential for faster data transfer and processing, having much lower latency. And with most stream processing frameworks, you can ingest data from a variety of sources, which produce the events, like these on the left here. I think that should be the left. And at the very end, most frameworks also allow you to publish data to different varieties of sinks, like a data store, various types of storage, or even to another data stream, like any of these here on the right. And in between is the fun part. So typically, data from one or multiple of these sources is written either to a log, to another data stream, or to a message queue like a Kafka or Pulsar topic. Then you have your actual stream processing application, using a framework like Apache Flink, Spark, Storm, etc. And as you can see, some stream processing frameworks are paired with local or occasionally external storage that enables the current application state to be stored regularly, similar to like a snapshotting system. This is referred to as stateful stream processing. This looks a little different depending on which framework you're using. So Spark, for instance, distributes the state onto a cluster and does most of the management there. SAMHSA replicates state across multiple machines. Generally though, and on a high level, being stateful means better fault tolerance as it can be used for updates or rollbacks in case of issues or outages. It can also be used for A/B testing and working in parallel with different versions. In Flink, they use checkpoints, which are a mechanism that copies the current state of each task after all the tasks have processed the same input. So in case of an outage or other killed processes, there are mechanisms that restart the whole app, and then before the tasks are started again, they're going to be reset to that last completed checkpoint. Frameworks like Flink also allow for querying on that application state, which is pretty cool. Okay, so now you're all stream processing experts. Awesome. All right, so we covered event producers or sources. We covered the queue, which is the log or initial data stream. We also covered the actual streaming application. And then of course the sink, where the data is eventually served up or published to. Awesome. Okay, so now the challenges of a system like this are that you're now ingesting unbounded streams of data, and you're regularly storing the state, if it's a stateful stream processing framework, of an application that is continuously consuming possibly massive amounts of data. And it never stops. At least you really hope it doesn't. It shouldn't. So all the benefits of stream processing, being able to push through huge amounts of data and super fast, all of these have what are probably some fairly obvious impacts on anything that's going to be downstream of your application or anything that's related to storage along that stream. Additionally, you could have a streaming application that consumes data directly from an initial source, but it's much more likely that the data you're consuming has already undergone several different transformations. It's also likely that your application is consuming from multiple different data streams, possibly even having to merge them. This means that you could be consuming data in multiple different formats, or possibly even have very different throughput rates coming in. It's also likely that your application is going to need to publish data out to multiple different sinks. This is actually extremely common, a very common stream processing scenario. However, full coordination with upstream and downstream teams, particularly in relation to metrics, is often overlooked. So overall here, the biggest challenge that I find with this type of architecture is that the relationship between an application in this situation and its technical ecosystem around it changes so drastically when that becomes a streaming application. So integration points become much more complex, which I'll be going into later, and structuring your metrics around those points and being able to keep those metrics meaningful without a lot of hassle, and when multiple different groups and teams might be sharing any one integration point. So that's what I really want to get into here. On a separate note, I think it's really important for systems to be provider agnostic, even when it comes to metrics. So because, if the product that logs, tracks, analyzes, and alerts on your data goes down, it would be really nice to have a backup for that too. So this could be as simple as maybe just having a JSON API that you can query as part of your system. So if the worst happens, you have redundancy for your logging and monitoring as well. For this reason, I'm going to try to keep myself provider agnostic in this talk as well. So you will see metrics from various different monitoring and alerting providers here. Okay, so metrics-driven metrics. How do you know what to measure to know what to start measuring? I know, right? And how do you get started, and how do you know what those right metrics are, especially if they change? Okay, so first though, you really do have to start somewhere, and often the best start is something really simple like measuring as much as you can for proof of concept or playground application, getting as close to production as possible, or even just a steel thread that just has those highest valuable features and behaviors. Starting that as a small cycle, growing it with the growth of your application's development. Great. So in addition, whichever framework that you choose is going to have its own recommendations for specific key components to measure. However, within this, it's really easy to get lulled into measuring just what's recommended, which is where data-driven development comes in. So later I'm going to have some examples of that specifically, where this metrics-driven metric cycle has really drastically altered how we measure that initial list of components. In the meantime, this is a really great example of a pretty full list of which Flink metrics to start with, most of which have direct equivalents in other frameworks. I'm using this dashboard as my example here because this provider does such a really great job at explicitly labeling what's important to track in stream processing, and specifically Flink. Like I actually literally wrote down a list, and then I found this image and I was like, oh, that's exactly what I have, which is great. I love when that happens. So firstly, Flink actually has a UI that includes pretty much all this information here with a couple additional things as well, including how many jobs are running, restarts, task manager count, etc. So on a high level, these represent most of the key components that actually keep Flink running. So if you're using another stream processing framework, you want to make sure that that's on your list, that you're tracking the equivalent of your running jobs. Very important. And one thing that I also really like about this dashboard is that you can see several different, completely different complementary pieces of your checkpointing all in one place. So failed checkpoints as a single number is useful, but combining that with the last checkpoint completion over time and over a span of a couple different hours, that combination is way more impactful. So I really like to show this in particular. So resource utilization, seen here in this column on the right. This is particularly useful for Flink, as a lot of the operations are dependent on the JVM heap. However, resource management for any stream processing framework is going to be very important because of that higher impact that a memory leak could have when you're continuously streaming in data. And I'll cover some of the rest of these metrics, like throughput, for instance, later on. Okay, so beyond all of those specific components that you can grab, you can measure those right from the start. When it comes to knowing where to start and what metrics are going to actually be valuable to you, I found that trying to have one single answer to these questions is just not very effective. Instead, I was much more successful when I framed this as a process, so an ongoing iterative practice of knowing your normal. The main components of this practice are super simple: focusing on what's meaningful, staying iterative, and keeping it accessible. As for keeping your metrics meaningful, starting with some good basic dashboard hygiene goes a surprisingly long way in enabling a process that will help you keep your metrics meaningful. Firstly, your dashboard should reflect the values and development priorities for the application that you're monitoring. This sounds obvious and sort of generic, but I want to emphasize that just how important this was for us on my last engineering teams for stream processing. With our non-streaming applications, we could sort of loosely adhere to this philosophy, and it just really didn't matter. But with stream processing, because of those extra complications, that extra impact, we found that this was much more essential for a variety of reasons. For instance, on an engineering team that I was on at another company, this was actually an example of the top of our main dashboard. And I love this one too. It's a great example of one that was really curated to have those metrics right on top that are actually going to be the most important to engineers and that are really the ones that are most driving that development process. There were more metrics below, but this is just the top half of the dashboard, and we were very selective about what went in that top half. Although we're also flexible. If the top engineering priorities changed, so did the dashboard, which usually just meant swapping out one chart for another that was already further down on the list. For this particular one, the stream processing Flink application, the consumption from our Kafka topics and our watermarks were particularly valuable, so you're going to see that at the very top. So watermarks in Flink, as with some other frameworks like Apache Spark, are a mechanism for controlling the duration of time that the application will wait for a record to arrive. This feature has many applications and is the basis for most event time operators. Watermarks often help determine how late records are handled, meaning it can have an impact on whether, what order, and how data is ingested into a stream. So it's important, but it's also something that's usually an estimated guess, designed by or designated by the engineer. So this is why it's really essential for us, at least in that early development of the application, to keep a really close eye on those watermarks, because this was a configuration that we were probably going to have to adjust a lot as we got more and more information about the data coming through. So a really good example of getting that metrics-driven metric cycle going. Next, each of our incoming data streams had its own lag chart. By taking some initial measurements of data flow, and analyzing how data was aggregated and the structure of that output, we were able to determine that some of our upstream teams aggregated and transformed their data completely differently than what we had expected, and that it even differed by team. So it was super valuable for us to place the metrics here for each team into groups based on how that data was aggregated. So just separating those out and really having that structure. So how this helped drive our development, though, was that once these metrics were in place and we had a better understanding of just how differently data was handled between different upstream teams, it naturally guided a restructuring of ownership. This information almost automatically redefined responsibility for integration points in a way that was based on the behavior of the software itself, which was much more efficient than how it had been structured previously. So next we have throughput and checkpoint size, which is our next priority. Throughput hopefully is an obvious one. You really want to have a good handle on how much data is going through your stream. We had our throughput separated out by which source the data originated from, which enabled us to have an overall view of the throughput throughout the whole system, but it also allowed us to click into a specific upstream application when needed. We also tracked throughputs at each reduce function throughout the streaming application, which I highly recommend. As I mentioned earlier, checkpoints, or in general, for any stateful stream processing application, anything that's related to how your state is stored, this impacts so many essential parts of your streaming application. So it should be fairly clear that your engineering team should be fairly familiar with what's going to be normal and abnormal for those components. So this dashboard, however, actually has a very unusual way of tracking checkpoints, which brings us to keeping this process iterative. So it's much more common in Flink to track the number of checkpoints, usually for a certain duration like the last hour, or for any anomalies over a longer period of time like a day. However, for our team here, at this point in the application's development, we are under certain restrictions for how we wrote our data to the sinks, and some sinks still needed to consume on a once daily cadence, like almost like a batch. So for this, we focused on the checkpoint size, which should follow a predictable pattern of steady growth and a single once daily drop for the situation. In this case, an abnormal drop or spike could mean that we were losing state, or in one case that there was a mismatch in how incoming data from different sources was being timestamped, which was like a whole very interesting thing. So overall, instead of being completely stuck on textbook metrics, which is a great place to start, it was much more effective for us to stay flexible. It was important to allow the data that we were receiving about our system, along with any other information that we had in our weird and unique system, and really trying to be data informed here, to guide modifications to our metrics, keep that cycle going, and even if that meant monitoring in very non-traditional ways. Okay, so you have a dashboard that has meaningful, prioritized metrics and supports iteration and flexibility, right? Yeah, yep, check, awesome. Okay, so, but they have to be something that's easy to use, especially if you get paged at 3 in the morning and you need to make sense of all those pretty lines and colors. So there's a lot of different techniques for this, but honestly, the most helpful thing that I found in thinking about this is scale. Because having the right things in the right order will definitely help with easy use, but prioritizing a list of 1,000 items is still 1,000 items. And especially with stream processing, that list can get long very fast. So this brings us to accessibility and the actual practice part of that metrics-driven development. There are tons of resources, I was gonna say a metric ton, sorry, and also tech blogs, etc., about how to be intentional with what to measure and why and where you put it. So a couple of my favorite quotes on this are, one of them was a Harvard Business Review saying, "It is simple enough to describe how to inject data into a decision-making process. It is far harder to make this normal, even automatic, for employees. A shift in mindset that presents a daunting challenge." Or more simply, a Tech Beacon article reminding us that you can measure almost anything, but you cannot pay attention to everything, which is a very hard lesson for me because I do want to measure all the things. However, my favorite quote was actually from another engineer that I was talking to recently about this, who said that any situation where people create their own dashboards without structure quickly starts to look like the cockpit of a 747. And I love this because it gives you such a great image of what this anti-pattern really looks like. And unfortunately, I'm guessing that we've probably all seen dashboards that look like this at one job or another. So I just really want to emphasize this is just a nope, just nope, nope, nope. So yeah, and with that, now we can move on to metrics as a shared language. So there was another great Harvard Business Review article that mentions that the biggest obstacles to creating data-based businesses are not technical, but cultural. More specifically, I like to think of it as that even the best data-driven development fails easily when it's only built for yourself. This fact is something that we could still basically ignore on most of the teams that I was on for all of our non-streaming applications. But as I've been mentioning with stream processing, those integration points are so much more complicated that you're likely to have much different relationship with those upstream and downstream applications and teams. So I feel like this is just really important to cover. When we built our first streaming app system at my last company, we found that people from all over the company suddenly needed a lot more information. Explaining the same stream processing and Flink concepts, re-explaining our streaming specific alerts, being included in incident resolutions that seemed maybe kind of far from our domain, all of these suddenly became part of our development process. Some groups, like other engineering teams, needed the same granularity as us, but filtered a little bit differently. Other groups needed to be able to pivot between summaries and depth, and still other groups needed full abstraction. And I like to use this diagram because it delineates these groups, but it also has the group in the center that needs the most in-depth technical coverage, and then the further you get out, the metrics and the way of sharing them become much more and more abstracted similar to that data-driven and data-aware circle from the intro. But it's really easy to forget that metrics are a powerful tool for communicating quickly and accurately across these different audiences, and is a really great way to help really minimize some of these issues and make them almost non-existent. So starting from the center, monitoring for yourself. I gotta say, this is probably the monitoring that we think about the most, let's be honest, and this may be the only monitoring that we think about. So I'm not gonna really get into this one because we've actually covered most of it already. So specifically, that was about where to start, those specific lists that we had, and also monitoring for stream processing by creating a practice of meaningful, iterative, and accessible metrics. So moving outwards, as for metrics for the other engineering teams around us, we knew that if everyone was looking at the same initial metrics, that no one would actually be getting the information that was useful to them, even if there are other engineers. So there had to be some sort of filtering or abstraction, but it really didn't need to be complicated. So most of this just revolved around a few additional basic data-driven concepts, including keeping our alerts small in modular units and using the language and tools of our intended audiences. In the end, we just ended up relabeling our alerts and monitoring with a tag for the specific team that it would impact, and using Slack integration for PagerDuty, Jenkins, etc., we just routed the alerts that pertained only to that specific team to a Slack channel that only had that team in it. We actually tried a lot of other things that were much more complicated and way more fun to program, but much less fun to use. So this ridiculously simple method scaled so much better than all of our other attempts, and it was actually able to keep up with that new complexity and any complexity that our downstream ecosystem came up with very minimal effort from us. I do want to give an example though, specifically for the added impact of upstream teams in the stream processing. So here's a slice from that earlier dashboard, our Kafka lag for each incoming system. So initially we were alerting on any spike in lag over a certain threshold, which the threshold we had selected because it made sense to us in the context of our data pipeline and based on the behavior of the majority of the streams we were consuming. However, although we have a great example of an abnormal spike here at 9:45 for 2 of the incoming streams in this example, so clearly that we definitely still needed that threshold, the spike in lag from 9:10 to 9:15 was actually normal for these streams. It actually would have been abnormal for the other streams that we were consuming, but because of how and when these particular ones published their data to us, this actually was their normal. So that was a pretty important thing for us to check with our alerting. A couple gotchas though. So when working around a predictable daily spike or drop, I've learned the hard way that particularly for upstream teams that use batch processing, that there needs to be a procedure to notify the teams along the rest of the stream if they decide to maybe change their collection or publishing schedule, because obviously that can have a pretty big impact. Or worse, autonomous teams don't always base their event time processing in the same time zone. So you could have a team using UTC and one, say, a time zone that maybe handles daylight savings time totally differently, like PST, and you could very suddenly be tracking or compensating for the wrong things. At best, you can get paid for something that's actually normal. At worst, your nice custom metrics are now working against you. So overall, this is an example where enabling metrics to continually guide how you measure and alert on your data, particularly around integration points for streaming, is so incredibly helpful, particularly for anyone that's going to be sharing that integration point. So I'm getting low on time, so I'm going to go through this one a little bit quickly. And basically here is an added challenge of abstraction and a group that typically wants to be able to pivot between depth and summary. So in speaking with people on both sides of this, both sides consistently emphasize the importance of using tools and language that are familiar to the target audience. As Noshnika Fee, a fellow developer advocate, said to me recently, the further you get from engineering, the more your status just needs to be a URL, but you'd be surprised at how far that gets you. And I gotta say, I've had a lot of success with that as well, particularly with something like a blog post with language that's catered to that audience, while embedding a few automatically updated charts or numbers into that post. So keeping it automated, but also keeping it in the language that works for them. So this part is the most abstracted from the topic here, and your metrics will likely have already been translated by a customer-facing professional at this point, so I'm not going to get into this one, but I do want to add it because I think it's important to include as a reminder that this is definitely still very much a part of your metrics picture. Okay, so with that, we've covered using metrics to drive your development process and how that looks different for stream processing, specifically keeping your metrics meaningful, iterative, and accessible. We've covered using metrics to minimize some of the human challenges that come with stream processing due to its unique impact on the rest of your technical ecosystem and integration points. Specifically, we talked about how to automate filtering and abstracting metrics in a way that work for different groups of people who share those integration points, and keeping it as simple as you can with techniques like small modular units and using the tools of your intended audience. And with that, thank you all so much for coming, and huge thank you to the DataEngBytes AU team. You've been amazing and really thrilled to get to be a part of this. Thank you also to everyone that helped out. Cheers.
Hey everyone, and welcome back. Caito, thank you for that talk and for joining us today for questions. We've got a lot of questions coming in the Slack, so I'm just going to dive right in if that's okay. The first one, what are some common mistakes or traps people can fall into when they begin to capture metrics?
That's a good one. So I think I'll start with the one that I have the most trouble with, is wanting to measure everything. And this is really honestly something that I need to remind myself constantly. I think there's definitely a time and a place, especially when you're first starting an application, for starting to build one, that can be really valuable. But I think it needs to be done still with a lot of intention. Especially like earlier I mentioned the dashboard that looks like the cockpit of a 747. It's just so easy to get that to be super, super messy. And particularly if you need to share your metrics. I think hoarding metrics is a big one, where you keep all the metrics to yourself. It's the one that I see a lot more often, I think, than you think, or maybe exactly as much as you think. I think also a really common one that's not very exciting, but is just one that I see a lot, is having confusing labels, because naming is super hard, especially when you end up with typically multiple applications that may have very similar names, and you have people who are not in your engineering org. So, I mentioned like the stakeholders, leadership, who may want to know information about that and may look at two metrics for two incredibly different applications that have very, very similar names for their metric labeling. So that's, I think, a pretty common one. But yeah, naming is hard.
Naming is hard. The next one, what are some good tools to capture streaming metrics and for visualizations as well?
Yeah, so that's a really good one. And I have my own preferences. So I'm just going to list them all and say kind of like what I like about each. So for Flink specifically, Apache Flink has its own UI, and it also has a platform that also now has a community version. And so that's a really great way to get very specific Flink metrics and be able to really look in all of the logging and everything in a way that really aligns well with Flink itself. One of my personal favorites is Prometheus and Grafana. So they just naturally are fairly easy to just like plug into Flink. But there's also a Prometheus connector for Flink as well. And there's actually another talk that's specifically on that that's really good that I can share in the chat as well later. And then there's also more kind of generic monitoring companies like New Relic and Datadog as well that, pretty much for stream processing, as long as you know what you're monitoring, you can use pretty much anything. But I would say that if your framework has its own monitoring, I think starting with that is really great. But I do think that adding something in addition to it, like supplementing that with something like Prometheus, that's going to give you a bit more of a full picture, having those two combined is really useful. So when I mentioned earlier being provider agnostic, I feel like I also should have mentioned maybe being able to be like provider complementary as well. So you're really making sure that you're measuring all the things that you want to measure. So.
Awesome. Well, and we've got another question from Slack, Caito. So as a developer advocate for Apache Flink, do you have the privilege to test the latest and greatest features that have been released, that are yet to be released? Bit of an insight into your role.
Yeah, it's pretty great. It's been really, really exciting for me. I've been a very enthusiastic Flink user for several years. And so getting a chance to actually be able to look inside that and see what goes out before it goes out is a huge perk. So that's been really great. As it is, it's with conference season, I haven't had as much of a chance to look at what's been going out like right now. But I've been able to see some things coming through that are pretty exciting. And I wish I could talk about them, but they're coming out soon. So
All under NDA.
Check the Twitter, the Verica Twitter for that.
Yeah, for sure. Probably a question that Karen's most interested in. What's the most surprising metric you've seen?
So I saw that and I've been thinking about this one. There's a couple that I'm not sure I can mention, unfortunately, but there is one that I know that I can talk about, which was we had one metric that didn't seem weird at the time, but the part that was weird about it was the behavior that it caused. So we had one instance in a previous company where we had this big data pipeline and we were ingesting from, the data was coming in from multiple different layers and originating from an agent that was installed on customers' machines. And one of the customers was incorrectly timestamping their data. And so we were getting event time stamps that were incorrect, and like completely incorrect with like real time at all. So it was like a really, really strange bug. And so that's the kind of thing that can really cause a lot of issues and be really hard to see. And so I think that was one that I remember kind of looking at that with my team and like, is this really happening? Like, is this telling us that time is not real? So there's a little bit of this, which I think is always sort of in the right situation can be really fun, and in the wrong situation can be terrifying. But it was a really interesting bug for us to find, where, especially for us, we're in a situation where we were writing once daily, which is unusual for our checkpoints. And so that was actually causing a abnormal dip, and which is also why I think it's so important to know your normal, because for us, we knew exactly what that graph is supposed to look like every single day. And it was so obvious when it was incorrect, because it was just, we knew it was supposed to look like, and it looked very different. And so luckily it was something we were able to catch really quickly. So even though the bug itself was super weird, and again, really was like, we had to look at like, okay, it is this o'clock. It says it's this o'clock in real life, because the event time was based on real time. So yeah, that was pretty weird, but fun because we caught it. Didn't hurt anyone.
Awesome. Thank you for answering that question. I love hearing about the weirdness of data pipelines. I think every data pipeline has its own weirdness to it. One last question. Do you recommend a list of must-have or non-negotiable metrics for streaming?
Oh, that's a good one. So I think it does depend a little bit on which framework you're using. But I think honestly, in general, really making sure that you're tracking what keeps that running. So for whatever framework it is, the components that keep that framework going and that keep your jobs running. So for Flink, that's going to be like your task managers, all of that. That's really important. So, is it on? Is it cycling? Are there restarts happening? That is super essential, because, anytime you're dealing with an unbounded stream of data, anything that's causing that to slow down or stop or act irregularly in the flow is going to be super important. So I think really thinking of it in terms of that, in terms of like where that data flow is going, what's impacting that is really important. Throughput is also part of that. So it's part of that data flow. And then after that, so there's memory and storage, which is super, super important. But then it starts getting a bit more specific to your application. So as I mentioned earlier, with our dashboards, you want to have the most important things that are really driving your development be your main focus. And for us, we actually swapped some of those things. So at one point it was memory management and really deep dive into our JVM heap as one of our primary things. And then once we got that to be super, super reliable, then that was swapped out for, I think it was actually swapped that specifically for getting a better view on our checkpointing. So I think it's more of there's a couple essential things, but then knowing that your essential things may also change based on where you are in that development process as well.
Awesome. Thank you for that. So thank you for answering all the questions. I think that's all the time we have for questions today. If you have any more questions for Caito, she'll be answering questions in Slack for the next little while. And feedback is important to what we do at DataEngBytes. So it's how we improve things and make the conference better for next time. So we'll be displaying a QR code next. And if you could provide feedback for this talk, that would be appreciated. Thank you.
Our next speakers are Joel Roland, who is a Solutions Architect Manager at Databricks, and Steve Lee, Principal Data Engineer at Atlassian.
An interesting talk in store for us today. Today, Joel and Steve are going to be talking about Delta Lake and how it can help solve some of your data engineering problems. Remember, if you have any questions for Joel and Steve, ask them in the Slack channel. With ETL and data ingestion made easy, please welcome Joel and Steve.
Well, good morning, everyone. My name's Joel Roland, and I look after the solution architecture team at Databricks for Australia and New Zealand. And I'm also going to be joined later by Steve Lee from Atlassian. And today we're going to talk about Delta Lake and how Delta solves some of the data engineering challenges organizations face today. Before we jump into Delta, just a quick introduction to Databricks for those that aren't familiar with us. And at Databricks, what we're trying to provide is a unified data analytics platform so that data engineers, data scientists, and data analysts can all come together in one location to help accelerate innovation across their organization. In terms of our company, we've got over 6,000 customers today and many different partners. And although a lot of people associate Apache Spark and Databricks, we certainly expanded our technology capability over the last couple of years. This is such as the introduction of Delta Lake, which brings reliability and performance to the data lake. And this is going to be the focus of our presentation today. We've got ML Flow, which is all around how do I manage the end-to-end ML lifecycle with ease. And then finally, a recent acquisition of Redash, which is for our SQL and BI analysts. So let's have a quick look at what the promise of the data lake was all about. And so the whole goal of the data lake was that we were now able to collect all pieces of information that an organization was looking for, whether this be structured, semi-structured, or unstructured pieces of data. And then we would load all of this into our data lake, and this could have been a Hadoop data lake with technologies such as HDFS, or a cloud data lake with technologies such as S3 or ADLS. And then once we had all this data together, we could then serve it up for downstream analytics and data science. But the challenge was that the data lakes were not really that simple to use, and there was many different reliability and performance challenges associated with them. So let's just go through a few of those. So if we think about from a reliability perspective, when you had production workloads that were running on these file systems, if these jobs failed halfway through, it was really easy to be able to corrupt the data stores. And so what that meant was that there was a heavy amount of engineering effort to go fix those. And also if downstream consumers tried to query while the data was left in a corrupt state, they would often end up with incorrect results. The Hadoop data lakes often got associated with this notion of schema on read, not schema on write, where we kind of had this philosophy of dumping all the data in and worrying about what it looked like later. But the challenge was this lack of schema enforcement really created inconsistency and low quality data stores for the downstream users of that data. From a performance perspective, we had this terrible small file problem, which means that if we loaded lots and lots of data onto the platform, or conversely had really big files, we suffered immensely in terms of performance when reading these data sets out. And then finally, to get the scalability and performance that we need, we had to partition our data. And partitioning, also nicknamed the poor man's index, meant that if we didn't know our data structures well that were used for the downstream analysis, or we were trying to structure our partitions around optimizing how we land the data, we often ended up again with subpar performance for those downstream queries. And then finally, as we wanted to expand out the type of capabilities on the platform, the lack of consistency on these data stores made it really hard to mix multiple different workloads. That means reading, writing, and trying to query out all at the same time. And so different patterns like Lambda got introduced and ultimately made our architecture very complicated. And so what this meant was that we had garbage that was landing into the data lake, garbage that was stored in the data lake, and then incorrect or garbage analysis that came out of it. So what is Delta Lake all about? And so as I said earlier, Delta is designed to bring reliability and performance to the existing data lakes, whether that be technologies such as HDFS, S3, or ADLS. Now, Delta in itself is an open format system based on Parquet, but what we're trying to bring is an additional capabilities such as transactional support, and also make the transition from the existing Spark APIs to Delta as seamless as possible to make sure that we can easily migrate workloads from existing technologies such as Parquet to Delta. At the end of the day, what this enables you to do is now bring in batch workloads, streaming workloads, and also capabilities that engineers love, such as updates and deletes, to existing file stores that didn't necessarily support these capabilities. Now, when we brought those all in Delta, this ultimately means that we can now pump out high quality and reliable data for our downstream analytics. So to highlight how Delta solves these various different challenges on the data lake, let's look at a particular use case and run through it. And so the goal here is what we're trying to do is look at particular airport and airline information and rank airplanes according to their flight delay schedules. And so this will need to combine 3 different data sets: a near real-time data set around flight information with a flight event history. We have a plane data set, which contains all current and historical information around an aircraft, which will be stored in a slowly changing dimension. And then a weather data set, which will contain public weather forecasts, which will be updated around every 5 minutes. And so the goal will be that we bring all these data sets in, we curate the data into a silver data store, and then we aggregate up this data for our ranking into a gold layer for querying and analysis. So let's have a look at what this looked like before we had Delta. And so we'd have our 3 different data sources, all of a varying different frequency of data being loaded in there, and different ways that we'd ingest those into the platform. And so for our near real-time feeds of data, we're probably using something like Kafka, and then a stream that's going to read that data in real time and then sync that data into Parquet into my flight silver table. For my plane information, which was a slowly changing dimension and stored in CSV format, I'm probably only going to schedule that on a batch basis as needed. And then finally, for my weather forecast that also gets ingested around every 5 minutes, we're going to use a JSON reader and schedule that on a basis, also storing both of these in Parquet files in our silver layer. We would then to create our gold layer on a scheduled batch basis, aggregate all of these 3 tables from the silver layer and create a new gold layer that has the delays per airplane also stored in Parquet. Now, do we anticipate any problems as we're going through this process? Well, let's look at some common different challenges and problems that might face along the way and how we help solve those. So the first one is, well, what happens if one of these production jobs fails halfway through? So let's look at the weather information. Let's just say we're loading this every 5 minutes, and on one of the runs, this data fails to complete, and halfway through, some portions of the data are left in this silver weather table. And so what this means is that this table is now left in a corrupt state. There's partial data that's been loaded into the table. And then for our gold level aggregates, that also then gets corrupted because the next time that the job schedules to aggregate the data from these 3 silver tables, this table will now also be corrupted. Now with Delta, we help solve this challenge by using ACID transactions. And that means either data loads and transactions either succeed or fail. And it means it's not possible for half data assets to be loaded into particular tables. The second challenge is around the lack of schema enforcement. So let's say we deployed a new job into production and accidentally introduced some incompatible schema changes. So in this example here, we're getting some new flight information. And as you know, there was already many different schemas that we might have available. But if one of these doesn't match this schema, what that would mean is that when we try to create this aggregate gold level table, this would also fail. And so what we're trying to do with Delta is avoid this happening. And so with Delta Lake, with schema enforcement, we can make sure that as the data is being loaded into the silver table, that only data that matches the particular schema and format is loaded in there, alleviating this whole issue of corrupt data and subsequent data failures for our downstream tables. The third challenge is lack of consistency. So what happens if we had multiple different jobs all running at the same time? So in this example here, we've got many different feeds of data and also some aggregate tables that are being created from these downstream feeds. And so each of these is on a different schedule. So it's likely that these are going to be concurrently scheduled at the same time. And so let's have a look at the example of, let's just say we're partially loading this weather data set that comes in every 5 minutes. But we also have another scheduled job that creates this gold level aggregate. If halfway through this write that's being progressed, we try to create this gold table, only partial sets of information that in this silver weather table would be available for this gold table analysis. And so again, we would corrupt this table by partially data sets being made available. Again, back with Delta, if we use these capabilities such as ACID transactions and also the ability to now do batch and streaming all on the same table, we alleviate these problems that are associated with consistency. The fourth challenge is, well, what happens if we have a data loss or a data problem? So in this example here, let's just say a new job is deployed into production that actually specifies the mode as overwrite, which means that we're not going to append this data set, we're now going to erase and reload it. And yes, this can happen because, again, people are writing code. And so this job would get deployed, and what would mean is that this flight data set is now disappeared. And so all of our historic data is gone and not available anymore. Now with Delta, we have the ability and a capability called time travel. So even if the user accidentally did do this overwrite mode, we keep a version of these tables inside Delta, which means that we can roll back to a previous version easily and restore the data that was accidentally deleted as part of this process. The fifth challenge is around the small file problem. So what happens when a lot of small files or small Parquet files start getting added to this silver layer? And so this is particularly prevalent in streaming workloads. So as we know, this was a near real-time stream of data that was coming in from our flight information. So imagine this is a stream that's continuously ingesting data, and every time it ingests data, it creates a new Parquet file. Now, the challenge is that we also have other small data sets coming in from our other feeds. And then when we try to then query these and aggregate those again for our gold level aggregates, it's really, really slow to be able to do this. So with Delta, we have a feature called compaction, which we can either auto compact when we load the data in, or we can batch compact that, depending if we want to balance our performance or latency. And then we also introduce a capability around data skipping, where in the Delta logs, we keep track of all the data that's being loaded in there, and we index the columns so that we know which information is relevant to what files. So that means that when we are doing those downstream querying on top of these tables, we can skip over data that's irrelevant to the queries that we're trying to access. The sixth problem is that, petitioning is static. So as we talked about earlier, often petitioning is either designed around the known query patterns when we create these workloads, or for ease of data ingestion. But what happens if those data access pattern changes, or when we load it for ease of ingestion doesn't match how our end users are wanting to query that out? Well, with Delta, again, we have indexing capability and data skipping. So what that means is that, again, we keep track of all this information separately to the Parquet files in the Delta log, so that as we write more selective queries or queries that only access subsets of the data, we don't have to scan all the pieces of information out of every single file. We know where that data is located, and we can more effectively and easily query that data out independently of whether that data was petitioned correctly or not. And then our final problem is around GDPR compliance. So what happens if we want to change an individual record? Now, again, these file stores are generally immutable by default, meaning we can easily append to them, but it's really hard to modify an existing file that's been loaded. Now, the great thing is with Delta is that we bring update, delete, and merge capability, meaning these type of workloads that were traditionally not possible are now able to be done with Delta Lake. So if we summarize those all up, how does Delta make this a reality for you to be able to use these particular capabilities? So in terms of, data appends, modifications, job stability, real-time blending of data sets, and keeping historical versions of data, ACID transactions really neatly covers all of these. And with this broad set of capabilities, have all of these data engineering problems covered off. One of the other big challenges is around the scalability and performance. And again, we use Spark under the hood to give us that distributed and scalable nature to manage the large amounts of metadata and files that we store in these Delta lakes. And the issues around the too many file problem, things like auto-indexing, really helps us get around the issue of reading what's relevant for the queries rather than every set of information that we have. And then finally, to resolve the data quality issues, the schema enforcement and evolution makes it really simple and easy to make sure that we have high quality and reliable data in Delta Lake. So with that, I'm going to hand over to Steve Lee from Atlassian, who's going to run through a use case of how they use Delta to help GDPR.
Hi, my name is Steve Lee. I'm a principal data engineer at Atlassian. Today, I'll be talking about how Atlassian are using Delta in our data lake, Socrates. First, a quick introduction to Socrates. Then I'll explain the problems we have been having with our traditional solution. Then I'll show you how we are using Delta to solve these problems. And finally, I'll wrap up with our future plans for Delta. Socrates is Atlassian's data lake. We have all kinds of data in our lake, including behavioral events, business intelligence, including financial and customer data, marketing data, and internal analytics data, including HR and incident and SLO tracking. Socrates is serving over 2,000 monthly active users. Socrates is built on a few core technologies. Amazon S3 is used for all data storage. Databricks is used for compute, including interactive notebooking, as well as ETL and job processing. And Redash is used for data visualization and dashboarding. How does Socrates handle personally identifiable information, PII? Well, we avoid storing PII whenever possible. We have a single lookup table of UUIDs to PII data. Our users can request temporary access to this table to perform joins with other datasets. The table is rebuilt daily from the source system in the identity team. This ensures users who have requested to be forgotten under their rights provided by GDPR are removed from the table. This solution seems to work acceptably. But what are some of the problems we need to consider? There are 3 scenarios. First, the right to be forgotten. This is mostly handled by the lookup table. However, this solution doesn't scale well. The second scenario is accidental data capture. Unfortunately, accidents do happen, and we need a process for cleaning up data that has been captured inappropriately. And finally, when a customer is deactivated, we need to ensure that any data they own is removed from the lake within 30 days. Socrates also avoids storing user-generated content for this reason. In the places where we do, we currently only keep the last 30 days worth of data to comply with this. The common theme here is that we need a way to selectively delete or update rows. So how would we do this in a traditional ETL world? First, we would copy the data to a new location while applying the necessary filtering. We verify that the filter has correctly removed the data we wanted. Then we create a backup of the existing data and then delete the existing data. At this point, our dataset is now offline. Now, we copy the corrected data back into the original location and verify data integrity. Finally, we can clean up the copies. Overall, the dataset was copied 3 times. This is slow, expensive, and error-prone. If the original dataset was being updated in streaming, we also have to stop ingestion for the whole duration of this process. Even if it was being updated in batch mode, we have to take the dataset offline during this process. There has to be a better way. And indeed there is. Delta Lake solves these problems. Delta Lake allows us to use natural delete and update statements. There is no complex data copying, no need to shut down the ingestion pipeline, no need to take the dataset offline. What does this process look like using Delta Lake? First, we perform a delete or update statement on the dataset. Internally, Delta Lake generates a new version of the data. When the data is ready, it goes live. Delta allows us to perform these updates and deletes in place. There are no multiple copies. Atomically, the dataset doesn't need to go offline and no one sees a partially updated dataset. And reversible. The backup is implicit in the version history of the table. Finally, we can use a vacuum statement to ask Delta to discard previous versions. The cutoff is configurable. For removing customer data, we would choose versions older than, say, 25 days to ensure we meet the 30-day deadline. To clean up an accidental data capture, we would remove all previous versions to ensure the bad data is permanently deleted. What about legacy tools? We still have a lot of users querying through Amazon Athena. The first option is an in-place conversion. After vacuuming all previous versions, you can delete the Delta log and the table reverts to being a plain Parquet table. If you prefer to keep the table in Delta format, you can use a manifest table. This is when Delta creates a manifest listing all the files that represent the current version of the table. Hive-based tools can use this list to read a Delta table. Finally, our future plans for Delta. Firstly, we would like to automate the GDPR cleanup tasks. Rather than rebuild the UUID table from source daily, we plan to subscribe to write-to-be-forgotten requests on our internal message bus and automatically issue delete statements. This approach should scale much better and allow us the flexibility to include PII data in other places. Finally, we want to use Delta Lake as the default format for all new datasets in Socrates. To achieve this, we first need to migrate the remaining Athena users over to Databricks, and we are currently rebuilding our streaming ingestion framework to land data using Delta format. We believe that Delta Lake is vital for the future success of Socrates.
Thank you, Steve. Well, I hope you really enjoyed the session that myself and Steve have run today. If you're keen to learn more about Databricks, we're hosting a virtual event on the 26th of August, a Unified Analytics Bootcamp, where you'll get an introduction to a little bit more around Databricks. Plus, we're also going to run some hands-on labs with Delta Lake and MLflow. So you'll get an opportunity to actually use the product and see some of the technology that we discussed in the session today. It's going to be running from 9:30 a.m. to 1 p.m. and you can use the QR code or the link on the screen to register. Hope to see you there.
Thank you and welcome back, everyone. So thank you, Joel and Steve, for being part of DataEngBytes today, and thank you for taking time out to answer some of our questions. And we've got quite a few coming through on Slack, so I'll jump right in. The first one, why the name Socrates?
All right, so Socrates is named after the Greek philosopher Socrates. And he created the Socratic method, which is a way of teaching people by asking them questions. So the idea was that you can learn things about data by running SQL queries on it. That's where the names come from.
Awesome, that's really cool. I love hearing the story behind names for things, because naming things is hard, as we heard earlier. Joel, you mentioned that Delta Lake uses Spark under the hood. As a data engineer who is using Delta Lake, how much Spark do I need to know day to day to run it?
Yeah, no, look, I think that's a really good question. And at the end of the day, what we were trying to do with Delta was give people with different backgrounds in terms of their technology skill set, different ways that they can interact with the platform. So if you're a data engineer that prefers working with Python and languages like that, that's certainly a way you can build that. But again, as we see more and more customers and people wanting to move workloads from more traditional based systems to Databricks, SQL and those type of approaches are certainly being more popularized. So again, if you've got consumers in your organization or developers that are only familiar with, say, with SQL and not some more advanced languages like Python, there's compatibility for those in the stack as well. So you can use Delta with more simple languages like SQL.
Oh, awesome. Good to hear.
Yeah, so Steve, could you talk a little on how much data you're currently pushing into Atlassian's Delta Lake implementation?
Sure. So at the moment, as I said, we are using Delta for our the PII data storage. So that's a relatively small data set at the moment. It's a few million rows. We are planning in the near future to start pushing much more of our data, including all of our clickstream analytics. So when that happens, that's roughly 1 billion events per day. It ends up being around about a terabyte per month. So we're not quite ramped up all the way yet, but hopefully very soon.
Well, that's huge numbers by any stretch, but I guess it is Atlassian. So yeah, another question for you, Steve. Are there any similarities between Apache Hudi and Delta Lake?
Yeah, definitely. They are both designed to solve the same sort of need, but there are some very different design choices that have been made internally. At Atlassian, we decided to use Delta because it was designed specifically to work with cloud storage systems like S3, whereas Hudi has been designed to run better with HDFS storage. There's also some differences in the way Hoodie writes files in I can't remember the terminology. They have two different storages, a read optimized and a write optimized, and they perform merges offline. This is a sort of a bit of a complication that we didn't really want to have. Delta always stores the files in the same format, just a standard Parquet format. It's a bit easier to then get compatibility with other systems such as Hive and Athena. So they're definitely designed to solve similar problems, the small files, deletes and updates. They've just taken very different approaches to doing it.
Awesome. We've got one final question that's just come through in the Slack. When do we choose between using Databricks versus Kubeflow when developing ML pipelines?
Sure, thanks for that. So look, I think, Kubeflow and Databricks are trying to solve similar challenges, I think, around the ML ops piece there. I think the big thing around Databricks is obviously what we're trying to provide is a platform as a service with all these different capabilities to help easily productionize those workloads as customers are kind of going from that experimentation phase all the way through to production. Kubeflow, obviously based off Kubernetes, does achieve some of those characteristics, but again, often customers have to bring it all together themselves. It's very hard to manage and build this all together. So again, a lot of our customers are looking for a quick start, easy way to get these into production without, again, all this kind of cumbersome heavy lifting that goes with the builds and deploys of these technologies.
Awesome. Thank you. Thank you for joining us, Joel and Steve. I think that's all the time we have for questions. So if you have any questions for Joel and Steve, they'll be answering some more questions in Slack for the next little while. And feedback is really important to what we do at DataEngBytes. It's how we improve things and make the conference better. So we'll be displaying a QR code next. And if you could provide feedback for this talk, that would be appreciated. Thank you. And thanks once again, Joel and Steve.
Good morning, everyone. Welcome again to Data Engineering Bytes. I'm Harmeet. I'm a data and ML engineer at ThoughtWorks Australia. I have special interest in streamlining core engineering practices in the world of data, as well as designing machine learning architecture that makes productionizing ML easy and scalable. Today, my co-host is Francisco. Over to you, Francisco.
Thank you, Harmeet. Glad to be here with you again. For those who didn't join yesterday, my name is Francisco Liwa, and I am a data engineer at Max Kelsen, an ML and AI consultancy here in Brisbane. I also co-organize the data engineering meetup here in Brisbane.
Our next speaker is Sam Harley. Sam is a senior solutions architect with MongoDB and is based in Sydney. Sam has worked in the IT industry for 15 years and is recognized as a trusted advisor to customers throughout Australia, providing best practice advice to assist in designing and building reliable and scalable solutions using MongoDB.
Sam is going to talk about how MongoDB enables real-time data with event-driven architecture. He will discuss why event-driven architectures are the natural evolution of how the world stores and accesses data, and show how MongoDB can assist in establishing an event-driven architecture using MongoDB Kafka connector. Ladies and gentlemen, let's welcome Sam.
Hello and welcome. My name's Sam Harley. I'm a senior solutions architect with MongoDB. And today I'm going to be talking about how MongoDB enables real-time data with event-driven architecture. To start, I wanted to really talk quickly about request-driven versus event-driven architecture. It goes without saying that the world moves in real time, and the demands on individuals, groups, and organizations are constantly evolving. Many enterprises and many customers that I speak to on a daily basis are still trying to meet their data needs in ways that don't match this new reality. To keep up with the pace of business, companies must become agile organizations fueled by applications that access, analyze, and distribute data in real time. These applications must run on a data fabric that offers the elasticity to scale up and down when needed, efficiently and cost-effectively empowering people with the insights that they need to do their jobs better. A traditional request-driven data architecture is an anti-pattern to this imperative. Request-driven architectures require users to make requests and wait until that requested information becomes available. An event-driven architecture, on the other hand, proactively makes a stream of data from source systems available in real time. Consuming applications and services can then subscribe to topics of interest and consume this data at their own pace. The key driver today in making this need for real-time data an organizational imperative is the emergence of microservices. Your ability to achieve the benefits of real-time data depends on your development organization rapidly building and deploying new apps, embracing agile ways of working, such as creating a DevOps culture and adopting a microservices architecture. One of the core building blocks of real-time is this concept of an event. And events have three key properties. They're atomic, so something's happened. The event represents that atomic unit denoting what has occurred. They're related, so an event rarely stands alone. It is nearly always part of a stream or a sequence of events. And events are behavioral. The streams or the sequences of these events create an accumulation of facts that capture behavior. So the way to enable companies to operate in real time is to help them capture, manage, and act on events as they occur. The smart organization that captures and acts on these events can predict and proactively prepare for what is to come. A cohesive model has emerged to enable organizations to best leverage events. Event-driven architecture. In an event-driven architecture, an application or a service publishes events to a queue, and that particular application or service is known as a producer. A subscribing application or service is a consumer. As we talked about a moment ago, producers proactively make a stream of data from source systems available in real time. Consuming applications and services then subscribe to these topics of interests and, importantly, consume this data at their own pace. There are many elements associated with an event-driven architecture. Event consumers listen for and react to events appended to topics. Event producers generate events that place messages into a message queue or stream. This concept of decoupling has many advantages, including allowing each service to evolve independently, enabling apps to go offline, and making the system elastic so that it can grow and shrink in accordance with ever-changing demand. Microservices communicate with each other through well-defined network-based APIs. The event streaming platform provides the channels and is effectively the glue that binds these microservices together, allowing events to pass between microservices and connecting microservices into complete applications. The database, of course, plays a pivotal role in event-driven architecture. Despite the fact that each microservice may have its own database, the core database provides a central repository, providing an end-to-end view of the business. So let's look at an example of this. In this figure, we can see an illustration of a price change that's occurred. The fuel cost to ship some items has increased, which may impact pricing. This produces events regarding that cost increase event and places them in the message stream where the event queue makes them available. All microservices are listening for any messages of interest. The pricing microservice consumes the event, analyzes it against existing data, and produces events conveying the new pricing into the message stream. The database then pushes these events back to our event queue such that it can be consumed by other services, things like your point of sale system, things like your marketing platform, things like your inventory application. Let's take a look at another example. If we think about fraud detection and remediation and the old way of doing things, effectively what we're talking about here is batch jobs that perform periodic data analysis. An identity thief steals a legitimate customer's credit card information and uses it, probably many times. After running a nightly batch job, the system flags fraudulent charges and notifies the customer. The next time the customer tries to use the card, it's declined. Customer calls the bank, learns the bad news, waits a couple of days for a new card to arrive in the mail. And while worrying about this situation, the customer may leverage another credit card, perhaps from another financial institution that the customer perceives as being less risky moving forward. So not only do you have a whole lot of customer pain, but you've also got a lot of business pain. You've now got to think about the cost to remediate and cover those fraudulent charges. You got to think about things like support time, effort, as well as resources involved. And that emergency intervention process takes engineers away from differentiating work, core projects and tasks. With real-time data, when a legitimate customer goes to use his or her card, the system is constantly checking for potential fraud. Seeing the transaction, the system sends an alert to the customer confirms the transaction is in fact legitimate and can continue to use their card without incident. The transaction is successful. Capturing and acting on events in real time in this particular scenario is the only way to effectively implement fraud detection and remediation. It also delivers a far superior customer experience, resulting in increased customer satisfaction, retention, and also enables things like future upsell as well as cross-sell opportunities for the business. So why MongoDB when you think about microservices and event-driven architecture? With MongoDB, data modeling for microservices is easy. MongoDB helps you to move at the speed that your users demand, giving you the power to launch new digital initiatives and bring modernized applications to market much more efficiently, running reliably and securely at scale, ultimately unlocking insights and intelligence ahead of your competitors. When we talk about MongoDB's intelligent operational database platform or data platform, there are three key tenets that we talk to. So the first one is this concept of the best way to work with data. The document model, the way we store information in MongoDB, is the most natural way to work with data. It is simple for any developer to learn how to code against MongoDB. And JSON documents are the language of APIs, which are how events are commonly communicated between individual microservices and enter the system. The database per microservice model adopted by many organizations today means that you may end up with a lot of databases. With MongoDB, that's not a problem. MongoDB Atlas is our fully managed database as a service offering, making it easy for you to stand up fully managed and automated databases. The second tenet we talk to is this concept of the ability to intelligently put data where you need it. We have built-in redundancy and self-healing capability available as part of MongoDB, ensuring that your business applications are always on for any user at any time. MongoDB can scale out your database horizontally to meet growing data volumes and user loads as you capture new market opportunities. You can also run your operational apps while also serving analytical workloads, driving machine learning initiatives, and using BI tools to unlock insights in real time. And finally, MongoDB provides you with the freedom to run anywhere. The MongoDB community offering, as well as our MongoDB enterprise offering, runs the same regardless of whether you deploy it on commodity hardware on-premise, on the mainframe, self-managed in the public cloud, on a mobile, or on demand as part of our fully managed database as a service offering, MongoDB Atlas. MongoDB is fast becoming the database of choice for developers. The total number of downloads of our platform have grown by a factor of 10 times from 7 million in 2015 to more than 70 million less than 4 years later. In Stack Overflow's 2019 developer survey, MongoDB was named the most wanted database by developers for the 4th consecutive year. We also recently released the MongoDB Kafka connector, which provides sync and source functionality for MongoDB. So you can use the Kafka connector to sync information into collections or tables, if you like, within MongoDB from events within Kafka topics. You can also use our source connector. So in real time, as data is changing in your database, using our change stream API, as you're inserting, you're updating, you're replacing, you're deleting documents in MongoDB, in real time, send that information downstream to a Kafka topic. Today, MongoDB is at the core of many event-driven systems. By starting with the core MongoDB data platform and binding in complementary technologies like Apache Kafka, MongoDB provides the data persistence heart of an event-driven architecture. And there are a number of other use cases that we can talk to when we think about enabling event-driven architectures. Things like time series and IoT use cases, predictive maintenance, being able to leverage MongoDB as an operational data layer, or potentially using an event-driven architecture to drive use cases like web activity tracking, as well as log aggregation. The MongoDB connector for Apache Kafka, as I mentioned previously, serves not only as a Kafka sync, but also a Kafka source. So if we take a look at that e-commerce example that we had a look at before, you can also then start to think about leveraging capabilities like our Spark connector, or visualizing data in real time using MongoDB charts, visualizing data in real time using your existing BI tools of choice using our BI connector. Change streams can then be leveraged in order to send data as it's changing in the database back to a Kafka topic, such that it can be consumed by other consuming applications. Ticketek, as many of you know, is Australia's largest sports and live entertainment ticketing company. Ticketek chose MongoDB over relational database technologies to power their core ticketing platform. MongoDB Atlas is the data layer for the event-driven architecture that supports their multi-channel ticket sales and distribution network. The platform also supports streaming integrations with customers as well as partners to feed real-time dashboards so that Ticketek can analyze ticket sales trends. Another customer example is EG, which is the UK's leading commercial property data service. EG has made MongoDB the center of its event-driven architecture and runs its business on a microservices-inspired architecture named pods. Each pod maintains a local instance of the data that it needs, pulling that information from a centralized system of record that stores things like transactions, locations, market data, property information, and all data product pods in the system of record runs on MongoDB. AHL is a subsidiary of the Man Group, one of the world's largest hedge fund investment firms. Man AHL uses MongoDB to create a single platform for all of its financial data. The system receives data for up to 150,000 ticks per second from multiple financial sources and writes it to Kafka. Kafka then consolidates and buffers these events before they are stored in MongoDB, where the data is analyzed by quantitative researchers. To sum up, by starting with the MongoDB platform and binding in complementary technologies like Apache Kafka, you can gain the advantages of an event-driven architecture, align your teams more effectively, innovate rapidly, and meet the challenges of ultra-competitive global markets. In short, you can run your business in real time. Thank you very much. I might open it up for questions now.
All right, thanks for the talk, Sam. It's very wonderful. It was very, very, very great. So we have some great questions for you today. So let's get started with the first one. So what are some challenges that one can face during production implementation of Kafka Connect with MongoDB?
Yeah, look, I think, a couple of things to obviously consider there. The first one is, whether you want to leverage just the sync as well as, the source connector for Kafka. Some challenges, that I've worked with customers through is obviously we store data in MongoDB in the form of binary JSON. So, if you're using our source connector, for example, and you need to transform that data, that's certainly something that some customers need to think about. But, predominantly it's about also, thinking with our source connector as you're updating, replacing, deleting, inserting data in MongoDB, making sure you're making use of things like the ability to perhaps only send certain types of events to a downstream Kafka topic, for example.
Cool. Are there any organizations which are using MongoDB Kafka Connect at large scale, and how are they doing? I mean, any challenges or what are their success stories?
Yeah, so we have a number globally. One of probably the most relevant ones here in country is a large insurer that use MongoDB and our Kafka connector alongside Kafka Connect to create a single view of everything platform. So an initiative that they as an organization had been working on for a long time was around how do we capture across all of our different brands, how do we capture that single view of customer, that single view of policy, that single view of asset, and they leverage MongoDB and Kafka Connect to do that. I think with our recently announced fully managed Kafka connector available as part of Confluent Cloud, we're also starting to see, more and more customers start to make use of those fully managed offerings like Confluent Cloud and MongoDB Atlas as well, which is our fully managed database as a service offering.
Great. Would you be able to share some use cases of MongoDB with Kafka Connect?
Yeah, absolutely. So, things like, I think single view is probably, one of the most relevant ones and topical ones right now for us. We find that, that problem around data living in all these disparate databases and a need for customers to move towards, more real time, to be able to do things like provide their customers with next best offers, for example, or much more tailored insurance advice in the insurance industry. So, things like single view of customer or single view of everything is certainly quite topical right now, through to IoT-based use cases. We're working with a large number of banks as well. So if you think of, and again, I think I spoke about this during my presentation, that concept of real-time fraud detection and everything else is, of course, top of mind as well. It is a fantastic use case, not only for MongoDB, but for Kafka and Kafka Connect as well.
Great. There's one question from our audience that as MongoDB is a master-slave architecture, and in case of failure, it may take some seconds to re-elect the new master. So how MongoDB can handle and provide high availability in such scenarios?
Yeah, great question. So the way MongoDB replica sets work is you have the concept of a primary node. And typically in production, we recommend that you have 2 secondary nodes. So what happens is out of the box, by default, the MongoDB drivers can only write to that primary node. And we're asynchronously replicating all those write operations to those secondary nodes. So in the event that primary node fails, an election will automatically take place, and one of those secondary nodes will assume the role of the primary. There are, things to consider here. So, typically what you would do is distribute those nodes across data centers or regions to maximize your availability. In the public cloud, of course, perhaps distributing those nodes across availability zones within a particular cloud region makes sense as well. Generally, from an Atlas perspective, where we have 3 nodes in a single cloud region across the availability zones that are available to us, we see that election process take place in under 4 seconds. Additionally, the MongoDB drivers are intelligent enough to recognize that election process is taking place, or a network partition has occurred, for example, and they will automatically try to reissue writes as well as reads exactly once as well.
All right, thank you for that, Sam. So there's a last question. Can ACID transactions be applied to multiple tables? Example, if one table fails, then roll back all other tables in the transaction to the last checkpoint.
Yeah, absolutely. So with MongoDB 4.0, we released MongoDB 4.0 2 or so years ago now. And with 4.0, we announced support for multi-document ACID transactions. So, if you think of the document model and the fact that it lends itself to denormalization, we've had ACID guarantees within a single document for a while now, available as part of the core database. But there are, of course, use cases where you want that transactional guarantee across documents or rows, if you like, within different collections or tables within MongoDB. And that was what that capability was all about. So we can provide those transactional guarantees across collections or tables, if you like, in MongoDB as of MongoDB 4.0. Prior to 4.0, what a lot of customers had to do was write a significant amount of application code in order to simulate things like rollbacks. But of course, now that's the responsibility of the database.
Amazing. Thank you, Sam. It was good to have you here. And to our audiences, Sam will be available on Slack to answer further questions. And we'll now have QR code coming up. So if you would like to rate Sam's talk, please scan it. Thank you.
Not a problem.
Hey folks, looks like we're running a good bit ahead of schedule. We might just have a quick little break for 15 minutes and we'll come back at 11:25. Probably just hop on the stream a couple of minutes prior to that just so that you don't miss out on anything. But we'll see you all soon. We'll play some funky music in the meantime to keep you going. Chat to you soon. Bye.
All right, welcome again, everyone. We will now have Larene Lee Gassick as our next speaker. Larene is a software engineer, meetup organizer, Microsoft MVP, ex-consultant, ex-computer vision engineer, ex-robotics engineer. Larene also tweets about accessibility.
Today, Larene is going to talk about inclusive storytelling with data. In this session, Larene will share a bunch of tips and examples to help you share your awesome data with the world. Let's welcome Larene for the talk.
Hi everyone, my name is Larene and it's my pleasure to be talking about making data visualizations inclusive and accessible to everyone. My Twitter handle is LareneLG and I tweet mostly about accessibility. I wanted to thank Peter and the amazing DataEngConf team, the wonderful sponsors, the other speakers and everyone who is attending. Especially in times such as these, it's really nice to be able to get together virtually and enjoy a conference, so thank you. There's a lot to cover in 25 minutes, so today I want to focus on the most practical things that I hope you can take away and apply to your job tomorrow. I'll spend a large chunk of this talk doing a live demo of how I build inclusive data stories, followed by a link to a list of data viz and accessibility articles at the end. In this presentation, I'll be channeling the concept of inclusive design. For those who haven't heard of inclusive design before, here's a quote from the Ontario College of Art and Design University in Canada. Inclusive design considers the full range of human diversity with respect to ability, language, culture, gender, age, and other forms of human difference. In order to be able to design inclusively, we must work against our unconscious biases. I am an able-bodied, young, middle-class, educated woman who lives in a wealthy country with pretty decent internet. I need to mindfully consider those who do not have the privileges that I do and how to design and build towards equal access for everyone. It's not easy and it takes practice, and we'll all make mistakes along the way. So what is digital accessibility? In this context, I'm talking about the skills and practices behind designing and building websites, apps, and content so that they can be used or consumed by people with disabilities. So you're probably wondering, how is it even possible to make data visualizations accessible for blind people and people with low vision? The whole point of it is that it's visual. When I started working on building live data charts around a year ago, I thought the same thing, that it was just way too hard. But I was determined to prove myself wrong. I know that designing for accessibility creates a better experience for everyone, and the best thing is that it makes sure that we don't exclude anyone. Another common misconception for those new to accessibility is that accessibility is only about building websites for blind people. As I mentioned before, designing for accessibility creates a better experience for all. Here are some examples. Being mindful when using color means that you don't exclude 8% of males and a small percentage of women who have some form of color blindness. Having high contrast and large fonts helps those with low or aging vision, but also makes text easier to read when you're walking around the sun trying to look at your phone. Using plain and simple language vastly widens your audience, and there's research to show that it's preferred even by highly educated specialists. When efficient and inclusive communication is needed, keep it short and sweet. Animation is a great tool in DataViz, but it's best kept to a minimum to prevent some people from feeling nauseous, and definitely don't use flashing colors that could trigger epileptic seizures. Websites that contain images with alternative text are essential for blind and low vision folks, but those websites also rank higher in search engine results. Subtitles and transcripts for video and audio are needed by those who can't hear, but are great for language learners and memory recall. And if you want to use text, and if you want to look for something specific that you heard in a video or podcast. Being mindful of keeping your file sizes small helps those in poor countries with high data costs be able to access online resources. With that in mind, let's begin the design session. Now, I do not have any formal training in design. I'm a software engineer full-time, but I have learned a few basic design principles throughout my career. What we build today won't look anything like something that might be on Information is Beautiful. Those data visualizations can take up to a whole team of data analysts, designers, developers, and journalists to create. So let's start by grabbing a dataset from data.gov.au. You can find plenty of great public datasets on there. This one is on school students with disabilities in South Australia. And what I did was I got the raw data and put it into Google Sheets, and below that I calculated the percentage of students with disabilities out of the total students. And let's start off by doing a little bit of work in terms of trying out a few different chart types, seeing what works best with the data. Here's a stacked chart. You can start to see some trends, but it's not my favorite, so I'm going to go back to the line chart. Don't forget to add a useful title. I'm just going to steal the one from the original data source. And this looks like a pretty good starting point, but we can do a bit better than this. So I'll save this chart from Google Sheets as an SVG and open it up in my image editor. I'm using Adobe Illustrator here, but any image editor will do. SVGs are really nice to work with because you can just grab the parts of the image that you want. So what I'm going to do is just grab the lines from the chart and copy and paste them into another design application I use all the time called Sketch. And the only reason why I've picked Sketch is because it's something that I'm used to working quickly in, so it's nice and familiar. I'm going to grab the grid lines as well because we need something to have a reference. And while we're resizing the chart, we don't have to be too exact. I'm not too worried about whether it matches up perfectly to the data. Someone looking at this chart doesn't need to know the exact percentage points either. And now I'm just going to start building the visualization in Sketch manually. So I'm putting the years along the bottom. The data was actually taken in term 3 of every year, but that's a little bit too much information. So let's keep it simple. Great, we've got all the years, that's looking good. So now we'll also put the percentages on the y-axis. I've made sure just to have the whole numbers, no percentage points, no decimal points. And since the highest data point is 3.3, let's make the axis go all the way up to 4% to give it a nice little bit of white space. So that's a pretty good start. I've made the lines a little bit thicker. I like how that looks. And instead of using a legend, I'm just going to grab each of the labels or categories and put them right next to their data lines. Note that the lines at the bottom are a little bit close together. So we'll just have to make sure that we put each of the labels in order. Just double checking we've got it right. So we need to do a little bit of cleaning up. We'll make it a little bit smaller. And make sure that they're all lined up correctly. Now notice the language and communication line is overlapping some of the other data points, so I've moved that label over to be as close to the line so it's clear that that is the language and communication line. So notice that the color of my screen has changed slightly. What I'm doing is using a color blindness simulator app called Color Oracle, and it checks for various types of color blindness. I've got Color Oracle set up so that I can press F5 to simulate red-green color blindness, or press F6 to see what the image looks like in grayscale. And this is really handy to make sure that I can still understand any diagrams or images that I've designed and make sure they are still understandable if a person cannot see color the same way that I do. So we're viewing our data viz using grayscale at the moment, and it's a really good way to double check that we haven't just used color to convey meaning. If we had decided to stick with color-coded legends, now would be the time that we would find out that it's not very accessible. Another tip is to just start off straight from the get-go working in grayscale and adding color later. So let's keep working on this. I'm not quite happy with it yet. Something we need to make sure that we don't forget is to include the data source somewhere in the visualization, or if you're including this visualization in an article, making sure to include a link to the source inside of that article near the diagram. I always like to include the link to the data source inside the image itself because it means that we don't forget to credit the source when we're sharing on something like social media. So now let's add a title to our visualization. Don't forget to make it nice and big. using plain, simple language. And I also like to include a subtitle as well. It's a great place to include any extra information that might help people to get an accurate understanding of exactly what the chart is talking about. I'm not too happy with the titles I have here, so I'm going to steal them from something I prepared earlier. So we ended up with a title of Percentage of Disabled Students in South Australia from 2013 to 2018, and full-time equivalent enrolments of students by their primary verified disability. Nice and clear and easily understandable what the chart is trying to show. So I'm going to keep tweaking the chart a little bit. I'm going to change the labels to match the color of their data lines, just to make it really clear which label matches which line on the chart. And something that I always do while I'm designing is to use an app or plugin that I've installed into Sketch to check the color contrast of text on its background. Web accessibility standards recommend that the contrast ratio between text and background should be at least 4.5 to 1, if not 7 to 1, to be really legible to those who might have low or aging vision. But high contrast also makes it easier for everyone to be able to read the text. The plugin I'm using here is called Stark, and I'll make sure I'll link to it for those who do use Sketch and would like to download it for themselves. I'm going to remove a little bit of redundancy from the labels to make it even simpler. The word disability is repeated a whole bunch in the labels, and we know that this chart is talking about disability, so I'm going to remove that. And just some finishing touches. I'm going to lighten the axes labels a little bit, just to really make the lines and the actual data stand out from the rest of the chart. And that's it. This is our final chart. Pretty cool, huh? So this is a great data visualization, but it's not quite data storytelling. Data storytelling is about using data visualizations to create change, and so we want to be able to tell a story with our data so that a person can come away from our visualization ready to act, make a decision, or even slightly entertained. This is a really good time to ask yourself why you are making this visualization. What is it that you want your readers or viewers to do after they've seen the visualization you've created? And this is the secret to making data visualizations accessible to everyone, including those who cannot see the visualization at all. So I've only been working with dataset for about 30 minutes, so I don't have any real observations. I'd like to do a lot more analysis before I can make any conclusions for sure. But let's say we had some findings about the two rising rates of primary disabilities here, speech and or language, as well as autistic disorder or Asperger's disorder. The first thing that I'm going to do is change the title to tell the audience straight away that this is what this chart is all about. Because the title is a bit longer, we can no longer fit the year on it, so I'm going to move it down into the subtitle. Since we're only focusing on the two growing primary disability rates, I want to make sure that the viewer's eye is directed straight to the two growing rates of disability, and I'm going to do that here by changing the color of the labels and the lines of the other primary disabilities to grey. I don't want to remove the other lines completely because I think it's still good to have them there as a comparison to show that these are the only two growing rates of primary disability. What I'm going to do now is add back in the two data points in 2018 for the growing rates of disability. And the reason why I'm doing that, because if you look at the y-axis, you'll see that the top number is 4%. And that doesn't sound like a very big number by itself. And since percentages are relative, it'd be great to have the actual raw numbers in there as well so that you can understand how many students we are talking about. So I'm adding to the graph that in 2018, about 5,800 South Australian school students had speech and or language disabilities as their verified primary disability, and 5,500 students with autistic or Asperger's disorder. So I'm going to add some icons next to the raw numbers just of a little person. And the reason why I want to do that is because I want to make it really obvious straight away that these numbers are referring to people. In hindsight, these probably weren't the best icons. They're a little bit ambiguous, but they'll do for now. I'm also going to round these decimals of the raw data points to whole numbers, just to not distract from the information that we're trying to share. So just shuffling things around a little bit just to see what looks better in the space. I'll make the labels on the 2 lines bold. And one last thing that I've done is I've calculated the growth rate from 2013 to 2018 of the 2 disabilities that we're focusing on, as well as the growth rate of the total enrollments. This is something that the audience probably could have worked out from looking at the chart, but I think it's great to provide these insights and save the audience doing the legwork. Adding annotations to the chart is also inclusive of the audience members who might have low numeracy and chart literacy skills. And this is something to be super mindful of if you are creating data visualizations for the general community. Always providing a text summary of the insights of the chart helps people who might not have great chart literacy, as well as those who can't see the chart at all. So in 5 minutes of analysis, we found some really interesting observations in the data. Since 2013, total students with autism or Asperger's disorder has doubled, and speech and language disabilities has increased 1.5 times, compared to total enrollments only increasing by 4%. Since this paragraph is one of the main takeaways from the data visualization, I want to make it as simple and as clear as possible. And one way of doing that is to use bullet points so that you can see straight away that we have 2 significant insights that we want the audience to take away from this chart. So we're almost there. I'm not 100% happy with the colors. I think that green is a little bit ugly, so I'm going to go onto a color palette website called coolers.co. And just look for one of the trending color palettes. I've picked a nice blue, and I'm going to change the color so that both lines are a shade of blue so that it looks quite nice on the eyes. And I'm just going to differentiate this summary paragraph from the other text on the chart. And how I'm going to do that is using a rectangle and giving it a bit of color behind it. And there's a nice bit of drop shadow on there as well. I can't decide if I want to go with a light color or a dark color. I might go with dark and change the font to white, and I'm just going to pick the same color as the dark blue that I just picked for the line. I'm pretty sure the contrast will be fine with that, the white text on a really dark blue color. Oops, just one more thing. I've used the abbreviation FTE in the summary paragraph, and so I'm just going to define it in the subtitle by putting it in brackets after full-time equivalent. And there we have it, an inclusive data story ready to share with the world. Actually, and you might have already guessed this, we have one last thing we need to do. Most data visualizations are saved as image files, so we need to make sure that when we share it, we don't forget to provide a text description for people who can't see the image. For those who are not familiar with alternative text, on the screen I have an example of the HTML code you would need to write in order to show an image on a web page. The alt part of this HTML doesn't change anything about it visually, but it does provide a description to assistive technologies. Probably the most well-known type of assistive technology is a screen reader, which is a software program that describes what is happening on your computer using a synthetic voice. But there are so many more types of assistive technologies used by people with different needs. And these technologies expect certain accessibility elements to be present in our websites and our apps. And this is why following digital accessibility guidelines, such as always including alt text for images, is really, really important. But sadly, due to lack of awareness, There is no alternative text available for pretty much over 2/3 of images on the web today. And also, one last thing I wanted to mention here is that not every blind person uses a screen reader, and not every screen reader user is blind. Just like not all deaf people know sign language and not all people who know sign language are deaf. Inclusive design recognizes disability as a continuum or a spectrum. People with similar disabilities can and will have completely different needs. So now that we know how to add alt text, how do we even know what to write? Describing a picture that's supposed to be 1,000 words in either a sentence or two really takes quite a bit of practice. The tip I usually give is imagine you had a blind friend or colleague sitting next to you, and you had an image that you wanted to describe to them. What would you say about the image? Luckily, data viz and accessibility expert Amy Cecil recently came up with a really easy to use template for adding alt text to charts. The template is chart type of data, where, and then you include the reason for including the chart. And then making sure to include also a link to the data source somewhere in the text so that the reader can go and explore the data themselves if they would like. And now that we have a formula for writing alt text for data visualizations, let's come up with one for the student disabilities chart that we just finished building. Adding text descriptions is the final step to creating accessible data visualizations. So I've also changed the subtitle and title to make it clearer that these are school-age students. I showed the chart to a colleague and had a discussion about it and realized that they thought the data was actually about university students. It's always great to check by asking for feedback when you're almost finished. So let's go back to the alt text. So here is the template. When we're adding the image, we'll add the alt text. So starting off with the chart type, we're using a line chart here. What is the data? The data is the percentage of South Australian school students and their primary disabilities. And the reason why we're including the chart, we wanted to show that rates of autism have doubled and speaking and language disabilities have increased 1.5 times between 2013 and 2018. And for more complicated graphs, it's always great to include a paragraph describing the takeaways. Not only does this help blind people, but it also helps people with low graph literacy. So this is the end of my main content for today's presentation. I've included the next 3 slides as well as a handy reference list of tips that I mentioned during my live demo, plus some extra tips that I wasn't able to cover. The first slide is all the tips I wanted to give you on chart design. The theme is keeping things simple, clear, accurate, and consistent. The next list of tips is related to inclusive design, being able to design for all humans. And the third slide is about telling a story. A few little things to remember to make sure that you are able to inspire action and create change. And one last bonus slide is also remembering to test with real people and not just asking someone if they like it or they think it's good. They're probably going to say yes to not hurt your feelings. But asking people to describe your chart back to you. And this might actually surprise you and help you to be able to communicate your message more effectively. And getting feedback is always really helpful and really important. You're not designing this chart for yourself, but other people as well. The best thing you can do is listen and have empathy and do as much as possible design with people instead of for them. So here are the links that I promised. I'll be sharing these links on Twitter as well, so you can find them later in case the slides don't come out anytime soon. The first link, bit.ly/dataviz-a11y-people, is a Google Doc that lists some great resources and also people to follow on Twitter who have been working in the data and accessibility space. And the second link is bit.ly/LareneLG-dataviz-a11y-slides, which is the link to the slides that I just presented. And thank you so much for having me today again. I really enjoyed putting this presentation together, and I look forward to hearing about your questions. But if you want to learn more about accessibility in general, I have a tweet pinned to my Twitter profile, so please check that out, and I'll see you soon.
What an amazing talk, Larene. I can definitely use these tips for better data storytelling. We have some questions for you. So let's take the first one. This is, are there any screen readers that can draw graphs and other visuals?
Thanks, Hamid, and thanks everyone for watching my talk. I'm not usually that serious, I just wanted to say. It's just, I'm a different person in front of a video camera by myself. So thanks for the question. Screen readers that can, I guess, able to decipher graphs. Graphs are usually just images. And so screen readers don't have kind of any special technology other than relying on the alt tags. There are some screen readers that do recognize or maybe some pioneering screen readers that are able to recognize using computer vision, but I think most of them are still in kind of research phase, correct me if I'm wrong. But there's also a different format to be able to publish graphs in digital, and that's using the image type SVG, which is HTML. So you can navigate that with the screen reader. So that's one place that is still a lot of room to explore in terms of making graphs really interactive and accessible to everybody.
Cool. Thank you, Larene. Just another question. Can you recommend some open source or tools which can help us do better data visualization?
Thanks, Francisco. In terms of tools, the reason why I use Google Sheets and Sketch was to show that you can do data visualization in terms of anything that you're comfortable with. I think Excel and Sheets are pretty widely used. And Sketch, unfortunately, is paid, but you can use any image editor to do that, even good old Paint. And there's a free one called Inkscape. And actually, a lot of people use Google Slides or PowerPoint to make visualizations and diagrams and graphs. So that's also good. But there's a bunch of tools online that you can search for to use for free in terms of making charts and data visualizations. I like Sketch because it's just so customizable and I'm familiar with it, but any image editor will do. And especially slide deck tools like Google Slides and PowerPoint are surprisingly really, really good for being able to customize things a lot.
That's amazing. It seems like we don't need anything fancy, just need those tips to do a better storytelling. Amazing. We have one more question. I think a couple of more questions. How did you start your journey with accessibility? And what tips would you give to someone who would want to start their journey of accessibility?
How I got started with accessibility. So I used to work for ThoughtWorks as well. And my first professional introduction to accessibility was on a first client there. It was an online pizza store, not the same one as the USA that just recently got sued for being inaccessible. They actually took accessibility very seriously. And that's where I was introduced to online standards and things. But I actually got unofficially started with accessibility because when I was born, that's when my father started to go blind. He's almost completely blind now. And so I grew up helping him use a computer with a screen reader. So I am really glad that I can kind of share insights with everyone, the developer community, of how we can make sure that we're inclusive of people with disabilities when we're building our tech. Because a lot of it is kind of the gateway into participating in society. So I think it's something really important to keep in mind.
Oh, that's an amazing background story, Larene. So we do have another question here. Do you have any example where you were able to make an impact, which you are really proud of after implementing the tips and tricks of inclusive storytelling with data?
Thanks, Francisco. In terms of making an impact specifically with inclusive storytelling with data, this is something I'm actually quite early in the journey. I've only started doing kind of a lot of work with data visualization and dashboards and things in web apps last year, and now I've joined a company where I have a I'm able to make an impact in terms of being able to decide how we're going to tackle dashboards and data visualizations and how to make it accessible. The impact that I've been trying to make is speaking and raising awareness as much as possible about how people not like ourselves use the web and use technology, and sharing with fellow developers in hope that because I learn a lot from everybody else, and I feel like I have something to offer in terms of accessibility and sharing awareness. And I hope that's the impact that I make, is raising awareness and showing people that it's a problem, because it's not really talked about that much, or it wasn't. It's actually getting more talked about now, which is really cool.
Cool. There's one question about Sketch, that can Sketch query data from a database to drive charts?
Oh, that's a very good question. Sketch does have the ability to plug in mock data for generating designs. I have not tried to actually make a data viz. I usually use it to mock up a data viz, and then I build it using something like D3.js or another data visualization framework, because that's my kind of, that's where I need to publish the data vizes that I build. But yeah, no, it'd be an interesting one. I'll have to check it out, and might answer that one a little bit later if I can find anything. But you can insert like text files of mock data that you can put in and have it generate your UI based on that, or your image based on that. So something to explore. That's a great question. Thank you.
All right, I think that's all we have. Questions for Larene. I think for the audience, if you still have more questions, Larene will be available on Slack for you to have your question, and then we'll have the QR code coming up now. If you'd like to have feedback for Larene, please scan it now. Also,
Wow, so many talks and amazing as well. So now we have Aiko Klostermann. Aiko works as a consultant and developer for ThoughtWorks. He's passionate about data science, software craftsmanship, clean code, and infrastructure engineering. He leveraged artificial intelligence to help clients gain competitive advantage. Recently, his focus moved onto infrastructure development for building data platforms to better enable client teams.
today, Aiko is going to give a talk on the topic artificial intelligence, more like artificial stupidity. Artificial intelligence does enable us to do really cool things, but even AI has its limitations. Aiko will show some examples where AI and ML have failed, and will explain why failures are unavoidable in ML, but also mention what we can do to reduce them in the future. Over to you, Aiko.
Hello, my name is Aiko, and welcome to my talk on artificial intelligence, or more like artificial stupidity. And what I'll be doing today is I'll be telling you a couple of stories. I'll be telling you stories about artificial intelligence. I'll be telling you stories about machine learning, and I'll be telling you stories about data. And some of those stories are success stories, but some of those are not. And we will in particular look at those who are not, and we will look at why they failed, and we will look at things how we can in the future prevent the same things from failing again. And when I say I'll be telling you stories, let's start with one of the greatest storytellers out there, which is Douglas Adams. And I'm sure some of you have read this book, The Hitchhiker's Guide to the Galaxy, which has brought us a couple of particularly famous memes like the one that the answer to the question of life, the universe, and everything is 42, and that we should not panic. And has been particularly popular in the tech community. And one thing that is not as popular, but Douglas Adams also introduced, is this Babel fish. It's this fictitious fish that lives somewhere in the universe that is tiny, and if you can put that into your ear, and what this fish does is it picks up all the spoken languages around you and translates that into a language that you understand. So any language in the universe, it gets directly translated into a language that you understand if you have this fish in your ear. And obviously that is fictitious, and it's a crazy idea. It's a fantastic but a crazy idea, right? That would never work in real life. Well, let me show you a little demo. Hallo und herzlich willkommen zu meinem Vortrag über künstliche Intelligenz. Now, if we look at this, right, this is almost as cool as putting a fish in your ear. I mean, admittedly, I still have to click that button, and we have to go to that website to translate it, and it doesn't. I could click this listen button and it would actually read it out, but I would still need to click it. But it's not quite there yet. It's not quite this Babel fish that you put into your ear. However, Google also sells these in-ear wireless headphones. And they use the same technology as the Google Translate page that we just saw, and they use the voice recognition. And what they do is, it is more or less the exact same thing as this Babel fish. Someone can speak something in a language that you don't understand. You still need a phone a little bit, but then the earphones do translate that and directly into your ear say the translation in, for example, English. So this fictitious fish, which sounded so absolutely amazing, right, is due to the use of AI and machine learning is almost already there. And that is one of the fantastic examples where AI and machine learning has definitely succeeded. And there are more examples. And this one in particular, I mean, the translation one is pretty good, but this one is life-changing, basically. Over the last couple of years, people have been developing image recognition systems for cancer. And in some cases, machine learning nowadays can predict cancer with a higher rate than human doctors can. So a couple of years ago, I think it started with breast cancer, and last year Google released a machine learning model that can, based on pictures that we can see here, for example, can predict that there are cancer cells more accurately than human doctors can. And I think that is something that is really impressive, and that is a great success story for machine learning and for artificial intelligence. But we all know, and especially if you think of the title of this talk, it doesn't always work that well, right? For example, this person on the very right is sending a tweet to Indigo, which is an Indian airline, and he's complaining about that his baggage went to Hyderabad while he was flying to Kolkata. And the response of Indigo, and I assume this is in AI, the response is, "We're glad to hear that." So obviously they didn't pick up on the sarcastic tone that the user was using here. And in the middle, you can see a screenshot of someone contacting PayPal and mentioning that he got scammed, and PayPal's response is, "Great." So clearly there are a couple of cases where AI simply fails, and not even difficult cases, right? And this one is one of my favorite fails of AI. And if you speak Mandarin, you could already figure out what it says there and figure out what was going on. For everyone else, I give you a little bit of a backstory. In a couple of cities in China, they have cameras installed at zebra crossing, at pedestrian crossings, cross streets, and when there's a red light, these cameras record the person crossing the street at a red light. They record the person jaywalking. And what they then do is in this case, what you can see here is a big screen. And what happens is if you get caught jaywalking with the camera, they show your face and they zoom in on you and they basically shame you and make everyone see that you jaywalked. And some other cities even have this system connected to WeChat Pay, where they record your face, they use image recognition, facial recognition, they figure out who you are. And when they know who you are, they know your bank account, they figure out your WeChat Pay wallet, and they immediately deduct the fine for jaywalking from your WeChat Pay account. Your WeChat wallet immediately gets deducted that fine. Right. And now with that background, if we look at this picture here, we can see this is not really a person crossing the street. What happened here is there's a bus which has the face of a person printed on it. In fact, this is the CEO of a company, and they're advertising with her on the bus. And the bus, like the pedestrian had a red light and the bus drove by. So the camera was pointing at the bus, seeing the side of the bus, seeing the face, and recognizing, oh, there's a person crossing the street at a red light, and then showed that face, zoomed in on that face and showed everyone, hey, this person just crossed the red light. And in fact, they even sent a message to this woman, which was a couple, like in a different city at that time. And when she got the message, hey, we just saw you jaywalking in that other city. And this is where, I mean, from a technical perspective, this is very interesting, right? Like having this facial recognition, having it connected to your bank account, more or less, is very interesting. From a different perspective, you could also say that if you let machine learning or AI decide whether you have committed a crime or not, is questionable. And this is a great example why it is questionable, because you can see that it also fails. We have seen other cases where machine learning fails, and you don't want to give it that much power if you can't be sure that it does not fail. So we've been talking about, or I've been talking about artificial intelligence and machine learning a lot. All of these terms have been hyped in the last couple of years, and lots of people are talking about them. And I think in the context of this talk, it would be good to have a common understanding of what, when I say these terms, what I mean by them. And we can start with artificial intelligence, and there's this definition that I really like, that comes from the Oxford dictionaries, which is, by the way, also the definition. If you type in Google, define artificial intelligence, you also get this particular definition. And this definition reads out as, artificial intelligence is the theory and development of computer systems able to perform tasks normally requiring human intelligence. And the important thing to note here is that it does not talk about any technical approach. When we get to machine learning later, we'll talk about technical approach. Artificial intelligence is a very broad term describing anything that a computer does that you would think takes human intelligence to do. And the chess program is a good example, where if you play chess against a human, you would usually assume that person, or if a person can play chess, you would assume the person has some kind of level of intelligence. Now, if you think about how we would implement a chess program, like a computer to play chess, it could be a relatively simple approach, right? You could just write a program that looks at the current state and then brute forces all the possible moves and subsequent moves to see which set of moves arrives as a desired state, which is winning that chess match. And brute forcing and a couple of if-elses is not a very sophisticated technical approach. It would, however, fit into this definition of artificial intelligence. So from my understanding and following this definition, artificial intelligence is a very broad term that just describes a use case where you would assume human intelligence is necessary, done by a machine. Machine learning, on the other hand, is where it becomes interesting. Machine learning describes a technical approach to solving a problem. And in machine learning, the algorithm to solve a problem is not actually implemented by a programmer. It's not implemented by a software engineer. The data you feed into a machine learning model defines the algorithm to solve that problem. You feed in different data and it solves the problem differently. You feed in more data and it solves it more accurately in certain cases, right? Like you give it some data, hey, this is the input data and I expect that output, and you do that a couple of times and it learns from that input data what output you are expecting. Neural networks is, as you can see, a subset of machine learning. And neural networks is just a way of building a machine learning model that is inspired by the human brain, or a biological brain in general, with neurons, and they're all connected. And deep learning, which surely you have heard, which is one of the most hyped terms in this whole broader topic. Machine learning is a subset of neural networks, of artificial neural networks, which just means that it has particularly many layers of neurons that are connected to each other. And so we've been seeing how these machine learning models fail, and one of the reasons why it fails is that they are just very complex. As you can see here, this is it's actually a very simple deep neural network. In real life, these deep neural networks can have thousands of nodes and 50 or 100 or hundreds of layers. And basically all these nodes do like some small computations, right? And they're connected, and the result goes into some other node, and that result goes into some other node. And they are, a lot of them are interconnected. In this case, all of them, they are fully connected. And I think the point here to understand is that these machine learning models that we use nowadays are so complex that it is virtually impossible for a human to understand why things happened in a certain way, why a certain input resulted in a certain output, why this model decided this and not the other way. It's so complicated that we can simply not see that. So that is one of the reasons why machine learning fails. Like you test a lot of cases, but you can never cover all of the cases, right? And there are clearly cases that will fail because you simply couldn't anticipate that the model would react in that way, because it's simply too complicated. And let me tell you about this other story, which is a great story from 2011. In 2011, there was the city of Boston. The city of Boston had a problem, and it was potholes. They had too many potholes in the city, and they wanted to find a way to solve that problem. And it was 2011. They did what everyone did in 2011. They built an app. So they built an app for that, and it was actually a pretty smart app. It worked in a way that people would install the app on their phone, then put the phone on the passenger seat of a car, and then they would drive around. And when there was some vibration and the phone noticed there was a bump, it saved the GPS coordinates of where the phone was at that time and sent it to the server of the city of Boston. So then basically the city of Boston could map where all the phones detected potholes and could go and fix them. Now there was one very interesting thing that the people found out, and it looked like only in the areas with the rich people, only in the high cost of living areas were potholes found. And clearly that is a very interesting result, right? Why would only in rich areas be potholes? And so the thing that people didn't think of in the first place was, it was 2011, a smartphone that could install an app was very expensive at that time. Not everyone had a smartphone. It wasn't as ubiquitous as it is now, where every 5-year-old child is watching TikTok videos on their smartphone. 2011 was a different time, and what that meant was only the rich people had the smartphone and installed the app. So the interesting thing here to note is there was no machine learning involved. There was no AI whatsoever, right? The thing that went wrong here was that the data was wrong. The data only came from a certain subset, of the citizens of the city of Boston, and that's what made the data wrong. There were obviously potholes in poor living areas, and they found that later out because they fixed it, which I also have to admit is particularly smart. they put the phone on the app in public buses and on garbage trucks that would basically cover the whole city. And that's when they figured out that there are also obviously potholes in areas with a lower cost of living. But the interesting thing here is to note that there was no machine learning, and yet it failed because the data was wrong. And now let me show you another example. Let's see what happens if I translate the following sentences from English to Malay. Let's say she is a doctor and he is a nurse. And there was something similar happened a couple of years ago and got popular in the Turkish translation. So why I selected Malay here is particularly interesting because Malay has Malay does have a gender-neutral preposition. So this she and this he that I'm using here in English results in the same word in Malay, right? So that it kind of loses the gender. And now we see how it translates into Malay. And if I now translate this Malay back into English, see what happens. Remember, I wrote she is a doctor and he is a nurse. If I translate that back, if I translate the exact same that we just received by translating it back into English, we get he's a doctor and she is a nurse. Now, how did that happen, right? Like clearly we saw translating it into Malay, the gender information got lost. But yet somehow now it is introduced again, but wrongly. Like we had she is a doctor and all of a sudden it's him. All of a sudden it's he is a doctor. And the reason for that again is the historical data that is being used. This Google Translate and other translation service basically read a lot of text. They have text in multiple languages, and they read both of that and then compare, okay, this sentence translates to that, and what they found in the historical text, in the historical data, that doctors were mostly male and nurses are mostly female. And based on that historical data, this is the translation that best fits this Malay sentence. And there's something that we can see that's clearly a sexist approach, right? Nowadays, we know that there's no reason why a woman can't be a doctor or a man can't be a nurse. But I think that again shows how, even though there is machine learning, this particular issue is based on the faulty data to begin with. And it was discussed some time ago, a couple of years. It became public when the same issue was found in Turkish because there's the same genderless pronouns. And what Google introduced then was they knew about that issue and they introduced both options, both gender options to show. Right. Let's talk about some other issues with data, right? There is the compass system. You have probably not heard of it unless you are in the US and might have been to court. This compass system is used in the US American jurisdiction, and it is, as it says, a correctional offender management profiling for alternative sanctions system. It basically, what it does is people who've committed a crime fill out a form, like 200 something questions, and based on how they fill out that form, this computer system predicts whether they will commit a crime again or not. And based on that outcome, the bail that they have to pay and the time they are going to spend in jail is adjusted to that. So if a judge sees, oh, it's very likely that that person commits a crime again, they the sentence that they speak will be higher than if the system would have said, this is a very clean guy, he won't commit a crime again. And obviously that fails, right? If we look here at the number of people that were labeled a higher risk but did not reoffend, So that is the false positive, false negative, well, however you want, right? You can see that only affected 23%. 23% of the white people got labeled higher risk and did not do anything. But almost 45% of African Americans got labeled a higher risk and did not reoffend. And if you turn it around, people who got estimated to have lower risk of reoffending but then did actually commit a crime again, that is particularly true. There's almost 50% for white people, and for African Americans only 28%. So what this means is that the data that is being put into that system, and there are very generic questions. There are questions that are about the neighborhood you live in. There are questions about your parents and so on. Based on that, and there's no information about whether people are Caucasian or African American, right? But based on the data that is put in, the system has a clearly a racist position against black people, where it is significantly higher percentage of labeling them as a high reoffending chance, and the same thing, the opposite is the case if you are white. And this system is still being used, and this analysis was done by ProPublica, and they that is very interesting, since there was no in this questionnaire, there was no mentioning of your skin color or your ethnicity whatsoever, but based on other aspects, the pseudo identifiers in a way the system figured out, okay, this is a black person, and then discriminated against them, and that is still being in use nowadays. And there are a couple of other situations. There's a study, as you can read here, that found out that self-driving cars have a higher risk of failing to detect dark-skinned pedestrians. And what that means is there's a car driving, self-driving, right? No driver. And what it's doing is have a couple of cameras, right? And LiDAR radars around to identify the environment, to not run into people. And these systems have a lower chance of registering dark-skinned people as pedestrians. That means if there is a white person, it is more likely to be identified and not being driven over, where if it's a dark-skinned person, there is a higher chance that a person gets not identified as a pedestrian and gets potentially killed. And I think that is, again, the reason for that is most likely that the data that was used to train those models, to train the image recognition, was mostly white-skinned people, and therefore it was not trained to identify dark-skinned pedestrians. And that is just that will kill people if that gets widely deployed. So basically, if you feed bad data into a machine learning model, it will react in a certain way. Right, and now you're looking at me saying, Aiko, you're telling us machine learning sucks, machine learning is everywhere, the world is on fire, are we all doomed? And I can tell you we are not. But there are a couple of things that we need to do. And when we decide on what machine learning model we want to use, we want to follow a couple of criteria. And explainability as a first-class model selection criteria is one of them. That means we need to understand why a model is decided in a certain way. For this particular case of convolutional neural networks, which is mostly used for image recognition, you can see here on the bottom, there is each layer, there's a form of visualization that lets you see what each layer is deciding on, what each layer is recognizing, and then making a decision based on that. In the other way expressed, what we need to change from our standard ML approach to an approach where we use interpretability and feed that into the model, and then train the model again. There's a technique that I that I really like, which is called LIME, which stands for Local Interpretable Model Agnostic Explanations. And what this does is it basically looks at your model, and it is model agnostic. It goes for various machine learning models. It goes for neural networks, and what it does is it tries to explain why things happen. And if we take, for example, this image recognition, where the image that we can see on the left was taken, and it was identified as a tree frog with a 54% score. And what this LIME then does is, and this is a nice visualization, it takes away certain data from the trainings data set, from the test data, and then see how what the model does predict. And what that means is you just throw out some data, and if it still predicts the same thing, you know the data that you threw out is irrelevant, right? The data that you kept is relevant, and you can see here on the frog, you keep the eyes and you keep the green face, and that is the relevant part. And if you see in the middle page, you keep the background, that is irrelevant for the prediction of this image. Another thing is we need more diverse teams. We need to have a different perspective on things, right? If you remember the autonomous driving cars, if there were more higher diversity in the team, maybe they would have tested for dark-skinned pedestrians on the pedestrian recognition system. Another thing that I really like is there's this data ethics canvas, which gets published by the Open Data Institute, and it basically lets you ask a couple of questions. Like, it has a list of questions, and before you start defining what model you want to use, you have to ask yourself these questions, like who you share the data with, what are the limitations of your data sources, and so on. Basically, a list that you can go through and see what you need to do. Sometimes you need to remove data. Do you really need, like, if you have racial data in your data set and you try to predict something where you don't need that information, should you just keep it in? Maybe just throw it out, right? It could, if you don't need that data, you can throw it out before it starts affecting your result. There's this other thing that I really like, which is open source visualization tool from Google, which is Facets, where you can just feed in data, and you can just select certain subsets, and you can see, oh, in this case, for example, 85% of my participants in that data were male. So clearly your data is skewed into that male category, and you have underrepresented females, for example, or other genders. And a similar thing is the what if tool, which lets you compare multiple models with the same workflow and integrates well with the facets system that I just showed you. And it lets you inspect a little bit how your model would react in certain ways. Yes. So I hope I could show you that there are a couple of issues with using machine learning, widespread machine learning algorithms, basically based on two things. Number one is that if you don't pay attention, you basically have a black box and you don't know how your machine learning model reacts. And in addition to that, your data might be skewed, and if you don't figure out where your data is lacking and what underrepresented groups you have, you might end up with wrong data. But I hope I also showed you that there are certain ways how to fix those problems. And with that being said, thanks for your attention, and let me know your questions.
Capture the mic. That was really a great talk, Aiko. There were so many interesting cases about AI and ML. Now we have some few questions for you. Okay, let's ask the question first. Are there any tools you can recommend which can help us decide ethics or fairness?
Yeah, I mean I mentioned two of them already in my talk, like the Google Facets, which is this wonderful tool where you can just throw in your whole data set and then look at particular subsets and see what data is overrepresented and where you are maybe missing some data points. I think one noticeable or one thing to understand is that when it comes to ethics or fairness, it is I mean, all these tools can only help us a little bit. The one issue that we're facing is that we haven't built moral into our machines yet. So the final decision, actually, what is ethical or what is moral, is a decision that we need to make. And in that, I think there are these tools like Google Facets or this what if that I also mentioned. They are all tools that help us identify or like understand our data a little bit better. And from that point on, we then have to make the decision in terms of ethic or moral or fairness. And this other Lime tool that I was talking about that looks a little bit into that tries to remove the black box behavior a little bit, can also help, where you then when you understand, when you have like interpretability of your machine learning model, then you understand a little bit more what data actually cause what outcome and what behavior, and based on that you can then see, okay, maybe I don't, maybe this is the data that I need to look into that is more or less relevant, and then go with that. But then again, yeah, all of these tools, there are a couple of others. All of these tools can only help us understand the data a little bit better. There's nothing that we have built moral into these tools yet, and I think that is the thing that we need to do is make humans more of a part of this decision-making process that currently is not really the case, or we are in the beginning of starting that. I think that is something that we need to do. Yeah.
Thanks, Aiko. In your talk, you mentioned that we can remove some of the data points, but that doesn't seem to be very easy. So would you recommend any strategies around this point?
Yeah, I mean, that was a very bold statement from my side. I have to admit that. I think the idea behind that is that oftentimes that data-centric systems are very data hungry in the way that they have incentive to just grab every data and store all the data about users, and that might not be ideal. There's a word in German which is Datensparsamkeit, which has made it into the English language, I guess, which means that you reduce the amount of data that you give out. Germans are relatively like, I don't want to sign up for something and give my email if I don't have a particular benefit from it, or I don't see the need for it. And that is something that I think is an idea that could be helpful. Just the idea that maybe I don't need to store all the data about this particular user if I'm only interested in a subset. And I give you an example. If you are, I think that actually is an example that Walmart did. So Walmart had some loyalty platform thing where they obviously, just like every organization nowadays, more or less stores as much data as possible. And I think they ended up storing racial information. Now, what value for a loyalty platform is to know about racial information about someone, about having that background? That is very unlikely to be relevant, and is more likely to actually cause harm, where you then end up with a model that is racially biased, right? So that is something that where you can obviously see maybe we can remove that. But then again, it's not as simple as I make it sound here. There are some obvious cases, but and I may have mentioned it in the talk, that there are these pseudo identifiers where you can defer, or you can get information about a particular person or about a particular user derived from other information. Like if you know where a person is living and that neighborhood has a particular high rate of people from particular ethical background, then you can make the assumption, okay, like to 80%, I'm relatively certain that this person has the same background. And similar, if you have, if you know where someone is living and you know there's a high cost of living area, you can kind of guess the income of that person. And these are, even though you don't have that particular data or you have removed it, you could still, it can still be derived. So in that case, it again, it's a little bit difficult because you can't just potentially know in advance what information you get out of this data. But then again, coming back to the first question, if you then try to have an interpretable model and see why your model decided in a certain way, you can maybe walk backwards and backtrack and see, okay, because I have this information, the model was able to derive that other information, and then get to the conclusion and be biased, and maybe by walking backwards, you would be able to remove the data that caused the whole misbehavior.
Well said, Aiko. So we got one more question from our audience. What I've observed is that with AI, machine learning hype is dying down. What we do in our data engineering work becomes distinct from what machine learning or engineers or data scientists do. What do you think?
Yeah, I think that's a very good question. I'm not sure whether machine learning or AI is dying down. What I think is that we are becoming more specialized. Like the whole industry and the whole idea of getting information, getting insights out of data has been growing crazily over the last couple of years. And that leads to people being more specialized. I mean, data engineering is something that has only become popular with the idea of that you have a lot of data and you need to process a lot of data that then later can be analyzed by other people. But without having a lot of data, data engineering would be less in demand. But the fact that we are specializing in, for example, data engineering is a sign that there's the industry to get insights out of data has been growing so much that there are areas that grow in itself, right? And I can imagine that there's, data security engineering probably grows in the next couple of years, right? And then there are a lot of my connections on LinkedIn are now machine learning engineers. 5 years ago, nobody was a machine learning engineer, and all of a sudden, like so many people. Like I think there's just we have, and there's this one statistic that I think is a couple of years old. But a couple of years ago, I read this article where 98% of the information ever created was in the last 2 years. Like the amount of data we create is so much nowadays, and that led to being able, or the industry being able to get insights out of this data so much more, that the demand for this is increasing, and with it growing, it specializes even more. And I think that's probably where data engineering is separating it from the machine learning part, and then the machine learning probably splits up in the next couple of years into, we already do that. We're specialists for NLP, and we have specialists for object recognition, and computer vision always has been a thing. So I think it's just separating the path a little bit because it is just growing so quickly.
Thanks, Aiko. It was, great talk and awesome insights. We're glad to have you. So audiences, Aiko will be available on Slack to answer further questions. We'll have a QR code coming up now. If you'd like to rate Aiko's talk, please scan it. Thank you.
Awesome. Well, thanks, Hamit and Francisco. That was really great. And also Aiko for that talk. That was awesome. All right, now for our final talk of the day and the conference, we have Kerry McRae, who is a solutions architect at Amazon Web Services.
Kerry will be taking us through a variety of AWS services, such as database migration services, Glue, and Athena in our talk on building data integration services for real-time on AWS. As always, if you have any questions for Kerry, head to her Slack channel and she'll be with us after the talk to answer them. Take it away.
Welcome everyone, and thanks for joining my session. Today I'm going to talk to you about building data integration services in real time with AWS. I'm going to spend a bit of time talking about some of the services that you can use, as well as the real use cases that we've seen when working with customers. I'll also take you through a specific architecture and demo later in the presentation. So let's get started. What we're seeing today is the trends with data is that it's growing exponentially. There's a lot more data for people to think about, and the data is a lot more diverse. It's not just structured data coming through, but there's semi-structured and unstructured data. It's growing at a rate of 10 times every 5 years, and that data needs to live a lot longer in an organization than it used to. The other thing we're also seeing is that there's more people who need to access that data. There's more roles, newer roles that have come up in the last few years. Data scientists, even applications need to consume data. And there's a lot more use cases that are coming about as a result of this exponential growth in data, including things like machine learning and scientific data analysis. So what are some of the use cases that we're seeing? So some of the real use cases that we're seeing includes things like hydrating a data lake. So if you've established a data lake, wanting to hydrate that data lake is really important. So wanting to do that in real time is even more important. Other data replication use cases we've seen, including disaster recovery and dev and test, or even transitioning from a batch analytics to real-time analytics is also another use case. The other use case we've also seen whilst talking to customers includes bidirectional data flows. So moving data from one SaaS application to another SaaS application. And there's probably many more that you can think of right now, but these are the ones that I'm thinking about immediately. So some of the services that you can use for data integration. The first one I want to talk about is Amazon AppFlow. Amazon AppFlow allows you to create data flows between SaaS applications and AWS services. So there's no coding required. You don't need to build custom integration services for these particular SaaS applications. It comes with data encryption, and you have the option to transform your data using these data flows in AppFlow. You can also schedule these flows to work on demand on a schedule or in real time, which is what I'm going to show you later on. These are some of the applications, SaaS applications that AppFlow is integrated with, and there's more coming, but these are some of the immediate ones that we have available within AppFlow right now. Another service I want to talk to you about is AWS Database Migration Service, and it's often not thought about as a service to be used for real-time data integration, and it's more commonly used for migrating databases from homogeneous database migrations or heterogeneous database migrations, but it's also available to be used for continuous data replication. It's low cost and it's really simple to use. So it has a simple UI that you can use. There's no installing of infrastructure. You don't need any drivers. You're purely using a replication instance, source and a target to be able to use database migration service. And it's also reliable. So you can use it in highly available architectures, and it has a self-healing part of the service that allows it to self-heal if there's a problem. Another service that's commonly used for real-time in AWS is Amazon Kinesis. So Amazon Kinesis is one of the main services we talk about when it comes to real-time data streaming. And essentially that's because you can use Kinesis for moving data in quick time from one service to another. So you're using Kinesis to form a data stream to move data from a consumer to another service. For example, from web clicks to, say, Amazon S3, which is what I'm going to show you later on in the demonstration. But it's also using it can also leverage other AWS services like AWS Lambda and Amazon Redshift. It's also quite easy to use, and it's a fully managed service. AWS Glue is a serverless analytics service that can help you also in real-time use cases. So it has a couple of components. It has the ability to crawl your data and create data catalogs. So it can also automatically infer schemas and populate a data catalog based on data that's stored in S3. It is serverless, so it produces and performs serverless ETL processes for you, so you can build workflows and execute jobs within Glue. And it also can orchestrate workflows for you. So it can orchestrate triggers, crawlers, and jobs, and it can automate a lot of that ETL pipeline for you. I'm now going to talk to you about the brief architecture that I'm going to walk through, and then I will show you a demo of what that looks like. So in this particular architecture, I'm using the Salesforce account, and I'm bringing data using AppFlow into AWS. I'm also going to include in this particular architecture a source database using DMS. I'm going to bring some data in to AWS, and then I'm also going to demonstrate some web clicks, so just randomly generated web clicks and data, and I'm going to use Amazon Kinesis Data Firehose to bring that data into AWS. All that data is going to be consolidated into an Amazon S3 bucket. And then from there, I'm going to use AWS Glue to crawl the data and create a data catalog. And the last thing I'm going to do is use Amazon Athena to query that data in real time using the catalog that Glue created. So having the data within Amazon S3 and querying that data in real time. So let's go ahead and look at the demo.
The first thing I've done here is log into the AWS console. As you can see, I'm in the North Virginia region, and the first service I'm going to look at is Amazon AppFlow. So this is the first screen you'll see in Amazon AppFlow. This service is used to integrate data from a number of different SaaS applications that you might be running. From this page, you could create a new flow or view flows. I'm going to view some flows that I've already created from earlier. The first flow I'm going to look at is a flow that I created that's going to bring in contact data from Salesforce, and I'm going to land that in Amazon S3. That contact flow is triggered on demand, so I'm going to run that. But let's have a look at it to begin with. So when I go into this flow, as you can see, it has an active status, it's triggered on demand. It has a connection to Salesforce that I've already established, and I have a destination bucket that the information will be loaded into. The flow is encrypted by default using AWS KMS, and it's a managed key. You could also opt to use your own keys. I've mapped a number of fields that exist in Salesforce to a destination which will become a file in Amazon S3. And if you have a look, I've run that flow a couple of times already, and I'm going to trigger that flow to run again. So while that's running, I'm going to now go and create another flow. And this time I'm going to bring in contact events. So that would be changes to any contacts that happen in Salesforce. So I'm going to give it a description. Salesforce contact events. As I mentioned, the flow is encrypted by default, but you can choose to use your own keys if you wanted to use your own keys. You can optionally add some tags here for the flow. For example, you might enter a flow that is for a cost center if you are using some billing data to bill the cost of this flow to another cost center. That's an example. Or maybe you wanted to understand the environment that this flow is used for. It might be a production or a demonstration or a UAT environment. The source will be Salesforce. Now, I've already established a connection to Salesforce. If you haven't done this before, you'd need to establish a connection to Salesforce, and you can do that by creating a new connection and entering entering the login details for your Salesforce account. That gives you the correct permissions to log into that account. So you would have to specify the name. I'm going to use an existing connection I've already established. So Salesforce has objects and events. The first flow that I created was a contacts object. This time I'm going to look for Salesforce events, and I'm going to choose look for contacts and contact change events. My destination will be Amazon S3, an existing bucket, and I will prefix the bucket with a Salesforce so that I know that this information is from Salesforce. You've got a couple of additional settings you can do here. You can aggregate records into one file. I'm going to add a timestamp to the file name, and I'm also going to place the file in a timestamped folder. And I'm going to select daily to make it easier. For the flow triggers, for the object flow triggers, you can use run on demand or run on a schedule. So the shortest schedule you can run is 1 minute. But for an event flow, it will run on the flow will run as a result of an event happening within Salesforce. And I'll show you how that works. This is where the real-time aspect comes into it. So you can optionally map fields, or you can use a CSV file to map the fields. I'm going to just map them manually, and I'm going to select all the fields because I don't know which fields are changing in the context. I can't add a filter because it's a event flow. I'm going to check all my options and then create that flow. I also need to activate the flow. So once you've created it, you then need to activate it because it's in a draft status, and you need to activate that flow to make that active. So in order to demonstrate that flow actually working, I'm going to go over to Salesforce into the contacts, and I'm going to make some changes here. So I'm going to make some changes to the email address of a couple of records, just to show you what the flow will actually do. This should actually trigger the flow to run as a result of these changes that I'm making to this Salesforce entries. So if we go back to app flow, we should actually see this event flow trigger. As you can see here, the event flow is now triggered because of those changes I made in Salesforce. And this is the real-time aspect of this event flow, where it's now processing the records, those 3 changes that I made, and it's pushing that data directly into S3. So you can see that's successfully completed. If we check the other flow as well, we should see that that successfully ran. Checking the run history, we processed it, and we have an additional record. So if we go into S3 now, and I refresh that bucket, I should now see a Salesforce folder. Great. And I see 2 subfolders under that, where one is related to the contacts data that I ran on demand for that flow. So you can see a file here has landed in S3. And the other folder that we have now is the event data. So I should, in theory, see 3 files processed in. Yes, I do. So if we check one of those files and just have a look at what that looks like. Let's have a look at this file. As you can see here, you can see a bunch of fields that it's told me has actually changed. So you can tell that it's telling me that the entity name contact was changed, the change type was an update, and that the email address was what was amended, and the last modified date gives me the last modified date. So that's really excellent information that we do often need when things are happening in our different applications. And that's AppFlow. The next service I want to look at is AWS Database Migration Service, and this service is often overlooked as a means to bring real-time data into S3, a data lake, or something like that. It's almost often used as a way to migrate databases, maybe from the same database to another database, or from one database to a different database type. But you can actually use DMS as a service to be able to do ongoing replication of data that's been changed in a database to, say, your data lake. So when you come into the service, this is the front screen that you'll see, and there's a couple of important parts to DMS. Firstly, we have things called endpoints. Now, in this case, I have an RDS endpoint, which is a source database that I'm going to use for this demo, and I'm going to create two additional endpoints, which will be target endpoints that will go into the existing S3 bucket that I've created. I also have a replication instance. So to use DMS, you need to have a replication instance, and that replication instance is what is used to replicate the data from a source to a target. And I've already created that already. And then in order to make the replication happen, you have database migration tasks. So I'm going to start by creating two additional endpoints. The first one will be the first S3 endpoint. I'll call it S3 raw target, so I know it's the raw data from the database, just a full load of the database. I need an IAM role to be able to run this task, which gives DMS access to S3, and I need the bucket name. So I'm going to use the existing bucket that I've already created, and I'm in this folder. It will be, I will prefix the folder with a path for tickets. I also want to bring in some additional attributes because I want the column names to be brought into the file, and then I'm going to test the connection endpoint. It runs in a VPC, so I'll use the VPC and the replication instance to test connection to the S3 endpoint. As you can see, that test was successful, which I'm now going to create that endpoint. I'm going to go ahead and create another endpoint now. I've now created another endpoint for change data capture. So this target is exactly the same as the first one I created. However, the subfolder that I'm pushing the files to is a different path in order to capture that data separately. Now I'm going to create two database migration tasks. One will be a full data load of the database, and the second one will be the ongoing replication of those changes. So I'm going to call this one full load task. I'm going to use the replication instance that I set up earlier. The source database is the RDS database, and the target will be raw, and I'm going to migrate existing data. I'm going to leave the task settings as they are, and I'm going to select a schema because I want it to bring in a specific schema from that RDS database. I'm going to leave everything else the same, and I'm going to create that task. So while that's creating, I'm going to go and also create a change data capture task for this same database, because I'm going to go and, as soon as I've created this replication task here, I'm going to go ahead and make some changes to the database. And as you can see here, the migration task is replicate changes, data changes only. So not all the data, I just want the changes that have been made. I'm going to select the same schema, and I'm going to create this task as well. So as you can see now, the full load task is now running, and that is essentially taking a full copy of that database, all the tables, and pushing that directly to S3. And the CDC task is now, that was starting, it's now in ongoing replication mode. So I'm going to go ahead and make some changes to the database to demonstrate how the changes will come through for those, the changes that I make to the database. I've now generated data in using a Lambda function to bring in some change records into that RDS database. So what I want to show you here is in the full load task, you can see in the table statistics that the data has now been loaded as full load rows directly into S3 using that first task. And with the CDC task, which is a change data capture task, which is now in ongoing replication mode, I've used a Lambda function to mimic some changes in the database. And what you can see here in the table statistics is because that's in ongoing replication mode now, it's using, it's effectively bringing in those changes in real time from that database directly into S3 for these two specific tables. And that's essentially how DMS works in terms of using DMS for real-time data integration. The next service I'm going to look at is Amazon Kinesis. So Amazon Kinesis is used for processing data streams in real time. The service we're going to look at is Kinesis Data Firehose. The first thing I'm going to do is create a delivery stream here. I'm going to call this web data. I'm just going to use some random web data that I'm going to generate through a website to show how you can process data in real time. And I'm going to use a direct put, which will go directly to S3. So I'm not going to transform any of the records, but you optionally can transform your records on the fly from using Kinesis going into S3. So if you have JSON format, for example, you could convert that record directly to Parquet and land it in S3 as a Parquet file, which makes it a lot easier than having to then do it later. And that uses AWS Glue to be able to do that. Or optionally, you can do other transformations using Lambda functions. I'm putting this directly into Amazon S3, and I'm going to choose the same bucket that I've been using till now. I'm going to put it into, let's just call it click data dash, and it wants a bucket for any errors. So I'm going to call that click data dash error dash. And the reason why I'm putting the dash at the end is because it will prefix it with the year at the end of that folder. So at the end of the folder name. So I'll put the dash in there. My buffer size will be 1, and the shortest time you can deliver the shortest interval you can select here is 60 seconds. So I'm going to select 60 seconds. You can optionally compress your data when it lands in S3. I'm not going to do that. You can also encrypt it as well. You'll need a role to be able to run this particular, so you need an IAM role. So you have the option here to use an existing role, or you can get it to create or update a role that it has for you. I'm going to review all these details and create delivery stream. So while that's creating, I'm going to go and generate some data that's going to push data through the Kinesis data firehose directly into S3 in real time. Now that that's created, that delivery stream, I'm going to go in and have a look. There's a couple of options you can see here. You can go into the monitoring tab, and this is going to give you information about how the files have been processed, the data has been pushed through Kinesis. So as you can see here, I've got a few metrics that have now popped up, which is giving me some information about the incoming records that have been processed through Kinesis. And as you can see, there's been 100% success rate in delivery to S3, and it's given me the number of records that has been delivered to S3. The other thing you can do here is you've got Amazon S3 logs, so if there was any errors, you could come in here and have a look at the S3 error logs to see, but I have none. So I'm going to now go into S3 and let's have a look at this data. So in this web folder that we have, I've got the click data dash, as you can see, that was the prefix, and it's added the year to the end of that folder name. So it will partition the data by year, by month, by day, and by hour. And I generated a number of files, but as you can see here, there's 3 files. So if we have a look at one of those files, you can see here, it's generated a bunch of random data for me. It's now being pushed directly in real time into S3. So it's great. So now that I've created all my data sets, I have my data flowing in real time into S3 from using AppFlow, DMS, Database Migration Service, and Kinesis. What I want to do now is I want to actually create a catalog of that data just so that I know exactly what's happening or where that data is coming from. And if I wanted to query that data, then I can use this catalog to query that data in a service like Athena. So first thing I needed to do was create a database, which I've already done. I'm now going to create a crawler. So I'm going to add a crawler. We'll call this demo crawler. You need to give it a name. I'm going to use existing data store. So I'm going to use S3, and I'm going to crawl my buckets my bucket that I created. And the first one I want to crawl is the contacts data. I'm going to add all my data stores in one go in this particular crawler. I'm not going to add any more data stores. I'm going to choose an existing role. If you didn't have an existing role, that you would have to actually create an IAM role that gives Glue permission to access S3 and the data stores that you are selecting. I'm going to run this on demand, but you can actually run it in a number of ways. You could do it hourly, you could even do a custom cron. For this one, I'm just going to run it on demand. I'm going to use the existing database, and I'm going to prefix this with raw underscore, so I know that this is just raw data coming in and not changed data. Review all those and finish. And I'm going to run it now. So while that's running, I'm actually going to go and create another crawler that will crawl the changed data sets that came in from Salesforce and from RDS. As you can see here, I've created another crawler that will crawl the changed data, and that was the data coming from RDS and also from Salesforce. And as you can see, the first crawler is now finished. It's now created 17 tables. Let's go and have a look at those tables. So if we have a look at those tables now, we can see that there is data, or it's created a schema for a number of these tables. So if we look at just one of them. So this was the contact data that was coming through from Salesforce. And as you can see, it's created it's used the column name that was in the file, and it's created a bunch of data strings for data types, for those particular, based on the columns that it's crawled. And it gives you a bunch of information here about, the amount of data in the files and any and where the information was located. And it's actually a JSON file. So if we look at one of the other ones, and that other crawler that's just finished as well, which is another crawler that I created for the changed data, you can see that that's actually finished and created 3 tables as well. Again, it gives you a bunch of information. It creates a schema. In this particular case, this is the Salesforce changes, and you can see here that it's brought in the changes, then it's brought in petitions for that data set, because that data is petitioned. And because it's a JSON file, it's used a struct data type for that particular file, and because it's a nested JSON file. So what we can use with those tables, now that we have a bunch of tables, we can actually query this data in Athena. So I'm in Athena now, and what you can see here is that when I connect to the data source, it's now connecting to the database that I created, and you can see all these tables available to you in Athena. And I can just query those tables as I would with any standard SQL query. So in this case, I'm just going to run a quick preview of the data for that particular table. I can also, that was a CSV file, and you can see it scanned it, and it scanned the data, and it tells you how long it ran for. I can even query, you can run any standard ANSI SQL query, but I could also even query this partition data that's nested JSON format. I can even query this type of data as well in Athena. And as you can see, that was the 3 records that I changed in Salesforce. You can see the email address and the record ID. And really that's it. And that gives you that opportunity to be able to, in very quick time, to be able to create data flows and bring in real-time data and then catalog that data and query it using a tool like Athena. And this is our AWS services.
And that concludes my demo for today. I really hope that helps you to understand how you can use AWS services to integrate data in real time. I'd like to thank you for attending my session today. I really hope you enjoyed it and have a lovely day.
And welcome back. Thank you, Kerry, for that insightful talk, and thank you for being part of DataEngBytes. We've got some questions that have come through in the Slack channel, so we might just jump right into it. The first one, you mentioned Kinesis and Kinesis Firehose, but how are they different?
That's a really good question. So for people who are watching, if you're going to use something like Kinesis Data Firehose, so within the Kinesis product itself, there's a couple of options there: Data Streams or say Data Firehose. Data Firehose is predominantly used when you just really want to, because it's a managed service, it's literally going to just take data from a stream and push it into something like S3, Redshift or Elasticsearch. But if you wanted to do something that a bit more custom, if you wanted to push it into a different application, or you wanted to use some sort of, like the connector, the Kinesis connector or the client library, you would use Kinesis Streams. The other thing about Kinesis Streams, it can actually store data for you. So whereas Firehose is just literally just pushing that data into another service.
Oh, cool. Thank you. Thanks for clearing that up. So any common pitfalls you see when people start putting together a solution like this?
I think the interesting thing about that question is that, as you could see there, I used a number of different services. And I guess the one thing about AWS is we provide lots of different tools available to different, ways to segment the way you want to do your data pipeline. So we've got lots of different tools. But I guess maybe one of the pitfalls might be trying to select the right tool for the right job. Even working at AWS myself, I find that there's lots of tools that you can specifically use. So finding the right tool for the right job is one of the pitfalls. And I guess maybe it's both a pitfall and an interesting challenge that you can use a lot of these services and understand if they're going to work for you based on what your requirements are, because everyone's requirements are really different. And knowing your requirements really well will allow you to select the right tool that you need to do what you need to do within your specific use case or your specific workload, and then being able to select that right tool which will do exactly what you need it to do. So for example, I use Data Firehose. It has a minimum delivery of 60 seconds, if you remember from the demo, and maybe you need a shorter delivery time, so then Data Firehose won't work for you, or maybe you need to push it to something else, so therefore you can't use Data Firehose. So I think one of the things is getting used to all the tools that are available, and sometimes that can be difficult across the platform. We have lots of services, but if you've got if you're not aware, as a solutions architect, we talk to lots of customers. So what I suggest you do is get in contact with your friendly solutions architect at AWS. We can often help you with that information as well.
Awesome. Thank you for that, Kerry. So that's all the time we have for questions. If you have any more questions for Kerry, she'll be answering questions in Slack for the next little while.
Yep,
and
happy to do that.
Awesome. And feedback is important to what we do at DataEngBytes. It's how we improve things and make the conference better next time. So we'll be displaying a QR code next. And if you could provide feedback for this talk, that would be appreciated. Thank you. And that was the last talk of the conference. It's been an amazing couple of days with lots of incredible talks. I feel like I need to go back and rewatch some of the videos in case I missed things the first time around. But it takes a lot of effort to put a conference like this together.
Yes, we have a lot of people to thank for today. As always, our incredible sponsors, Cloud Shuttle, ThoughtWorks, Canva, Databricks, Snowflake, Fivetran, Amazon Web Services, Confluent, Yale Conferences, MongoDB, and Microsoft Azure. The organizing committee, thanks for all your help in getting the conference up and running. Really, you've done a really great effort. Our selection committee of Roland DePellier, Greg Root, Ingrid Anzola, and Jess Flanagan, our wonderful selection of talks. I think we've had really good feedback from our talks. All of the speakers, we've had some amazing talks over the past couple of days from some incredibly talented people. A big thank you to all the speakers and for being part of DataEngBytes conference. And finally, a big thank you to you, everyone who's been here watching the talks. We hope you've enjoyed the conference and we look forward to seeing you at the next DataEngBytes event. For now, see you again. Thanks all.